All right, I think we're going to go ahead and get rolling here, everyone. So I've mentioned the Hope Station several times. We're very excited to be working with Protoplanet and the Mars Society of Australia on this project. And this morning we have with us the core team of the Hope Station. Siddharth Pandey is the CEO of Protoplanet. John Clark is the current president, I believe, of the Mars Society.
Former president.
Former president of the Mars Society Australia. And Analia Patel is also a member of Mars Society Australia. And John and Analia served on the first crew of Hope Station just recently. So welcome to the conference. We'd love to hear what you guys have to say this morning. Thank you.
Okay. So Siddharth, can you start the slides, please?
Sure.
While we're getting started, Siddharth is also the recently appointed Vice President of Mars Society Australia. So very briefly, the Hope Station is a project of Mars Society Australia in conjunction with the US Mars Society and our Indian partners. We have Indian partners to facilitate operations in that country, Protoplanet, which has been set up by Dr. Siddharth Pandey just in the last 12 months. And we are working in Ladakh. In the US, we say, where the hell is Hankville? Well, in Ladakh, we say, where the hell is Ladakh? It's the extreme northwest corner of India, bordering on Pakistan to the west and China to the north. It is a high altitude, cold desert, which is why it's been chosen as a Mars analog by us in 2016 for our Indian research. Next slide, please. And the key area that we've been working in has been the Soka Basin. Soka is a high-altitude salt lake, about 4 hours from the capital of Leh, and is one of the most remarkable spots I've had the privilege of visiting in my career as a geologist, and particularly as an analog scientist. And next slide, please. So here's a view across the basin, not far from where we have established the Hope Station. We are at an altitude of 4,500 meters. Ultraviolet is nearly twice what it is here at sea level. Air pressure is about half what it is at sea level. And as you can see on the lake here, that's not ice there, that is masses of salt. Next slide, please. These are the attractions. As a high altitude cold desert, it's an early Mars analog. It is set in a basin, which makes it a crater analog. It's not a crater in itself. It's a tectonic basin, fault bounded, formed during the uplift of the collision zone between India as part of Gondwana land and Asia to the north. The fault-bounded basin is about 20 kilometers across, and there's 1.5 kilometers of vertical relief. So the snow-capped mountains in the distance are at about 6,000 meters or a bit more. Beneath the lake basin in the distance there's over 500 meters of sedimentary fill, just like in a Mars crater. As I mentioned earlier, we're at 4,500 meters of altitude. Air pressure is 540 millibars, or hectopascals if you prefer, roughly half an atmosphere. UV is intense. It's twice what we have at sea level, so you've really got to be careful when working there to make sure you're covered in the appropriate protection. Temperatures are very extreme. I've only been there in summer. They can rise to 30 degrees from the intense sunlight. At winter, it gets down to about -40. But unlike, say, the Arctic station up on Devon Island, you always have sunlight. It's a normal daylight because you're just outside the tropics. The salt lake is not an ordinary salt lake. If you pick up the salt there, it looks like powdered snow, and you lick it, it doesn't really taste salty. And that's because it's actually sodium sulfate. And these sodium sulfate minerals we find on Mars, thanadite and glauberite, and also on the moon of Jupiter, on Europa. And they appear to be salts that are extremely useful in preserving biosignatures. So it's a very interesting salt from and salt lake from an astrobiological point of view. Not that far away from the lake, half an hour's drive, is a hot spring system. Water's boiling at 85 degrees because of the altitude. And it's a boron-rich spring, which we know from early life habitats here in Australia is an environment that we find the earliest signs of life on Earth in. And it is thought that boron-rich hot springs are able to facilitate the synthesis of nucleic acids such as RNA. The landforms themselves, we've got glaciers and former glaciers coming down from the mountains. We've got permafrost. If you dig a hole 1.5 meters deep, you start running into ice in the subsurface. And there are receding shorelines. So just like in crater lakes on Mars, they're surrounded of this age from early Mars, from 3.5 to 4.5 billion years ago. The SoCal Basin is surrounded by receding shorelines, alluvial fans feeding into the residual water in the bottom of the lake. So without further ado, I'll now hand over to the project director and MSA's Vice President, Siddharth Pandey.
Thanks a lot, John, for that great introduction. Good morning to everyone listening in. And I also wanted to acknowledge both John and Annalie as great mentors and advocates for astrobiology and analog research in India over almost the last 1 decade. And it's a privilege and an honor to continue working in the capacity of a vice president at Mars Society Australia, and also get help as we are moving towards establishing an India chapter for Mars Society. We have been in touch with several groups, but Protoplanet was the result of the culmination of a decade-long effort that has been worked upon by several groups of people, both in India and outside India. So I will try to spend the next 10 minutes giving a quick run through into the activities that eventually led to the commissioning of the Hope Station this year. But it was important for me to set that context and background to help people understand that there's been a lot of different stakeholders and movers and shakers that have made this happen, made this possible, and we are coordinating that effort. But it couldn't have happened without support from several ends, including, of course, the U.S. Mars Society very recently. Ladakh has been a training ground for Mars Society Australia for several years. Even though we lead Mars analog research activities in Australia, we have been utilizing the environment and the training opportunities for people in Australia, ranging from students, early career to mid-career researchers, and also senior researchers. And what I've done on this slide is just put some photographs and just a table of individuals who have traveled over to India as part of different field expeditions, and acknowledged a lot of those individuals, starting from 2016, whether those are educators or graduate students, PhD students, postdoc researchers, fellow collaborators. It's led to a lot of learning as well as training together in the field in Ladakh that has culminated in the efforts that John, I think, alongside Annalie and a few others in India, we envisioned this in 2016, that we need to have a station for the long duration experiments, for supporting scientists in the field, and also to kickstart analog missions, isolation studies, as well as interdisciplinary groups of humans working in the outdoors, and giving opportunities to students in India and the neighboring countries who otherwise would have to spend a lot of funds to reach places in the US. So this is just a representation of the different mission logos of expeditions that have taken place. Over the years, the missions have increased our understanding of the region, and they've also helped us gain a lot more confidence for conducting long-term analog studies. I think one of the points that um, we did not immediately get to was this is one of the most challenging environments where you could be conducting analog studies. Given the high altitude and remote conditions, it's not as remote as perhaps some of the, for example, the station in the high Arctic, the FMAR station, but it does bring with it a lot of diverse environments, and each of those environments bring with it a lot of safety hazards and logistical challenges. So for us to be able to build a station, it actually has taken years of experience building and training of logisticians and operators to be able to reach this, to reach this place. Even this year, we conducted Space Bound India, which is a program that started off at NASA Ames Research Center, and it went international several years ago. And after 2016, we conducted the second Space Bound in India in 2025, in this summer. And this is an expedition that brings together senior, seasoned field expeditioners with scientists and engineers and students who are new to the field, and has them working together, planning out their day, conducting, simulated dry runs in the hotel lobbies and over breakfast, and then eventually putting together instruments and taking them out in the field. One of the individuals, Dr. Steve Hobbs, from Mars Society Australia, a former director, was able to bring through a rover this season as well. And it took several months of training remotely and eventually bringing and conducting those analog expeditions. We see him here sitting with the Sokar Lake right behind him in the distance as well. And there's other forms of expeditionary work that takes place. You collect samples, explain students the context within which whatever they're observing and seeing. There's a lot of geological, narrations that are given, things like discussions that take place on the rooftop. So Ladakh has led to the development of careers of students from different disciplines. And I think, the station coming together is actually building upon that it's not any stranger to training students and engineers, engineering and sciences. So with this, I'm very pleased to present to the Mars Society Convention the Hope Station, Himalayan Outpost for Planetary Exploration. And it's a formal partnership between the US and the Australian Mars Societies. In India, the Indian Space Research Organization, we have a formal partnership with the Human Spaceflight Center. And we also are working in close partnership and guidance with the Union Territory of Ladakh and the Ladakh Autonomous Hill Development Council. So these are the organizations that will have a permanent representation and presence to run the station. And we started several months ago with a very serious effort of putting together a semi-permanent outpost, and we worked together to design the station and also start identifying, based on the terrain in which we are, some of the scientific activities that we would like to conduct. Now, this is a screen grab from a hyper-realistic rendering that we had a team member produce for us. And this is what it looks like several months after that. So to go from a simulation to an actual reality took several weeks of sleepless nights, and a team of over 20 to 25 construction workers, engineers, geologists working together in a very rough terrain with sparse resources. And putting the station together was no small feat for us. It actually was the effort that came bore out of several weeks of planning. And the environment being very similar to a space mission in the ways that there's only so many spares you can carry with you when things break down because of dust and static buildup, or human performance starts fading very quickly in low oxygen as well. It was actually quite an incredible effort that would not have been possible without the support of senior members like those like John and Annalie and others, but also of some very hardworking people in the field. This is just a quick drone footage built to give people some understanding of the environment that we are in, where the station has been built. John has already given a high-level geological context of where we are, but the site had been chosen after a site selection criteria wherein we were looking at not just the scientific importance, but also logistics, which drives a lot of these things. It had to be remote, but at the same time accessible. We had to find a place that would interest as many scientists and engineers as possible so that we would maximize the use of the station. And we are also very conscious of the environment in which we are. What you're looking at is the first iteration of the station. It was commissioned 2 months ago, and it's in a state of further upgrades. We are completely off the grid, completely solar powered, and we're managing our own waste. So the waste, which is human waste, is being collected and not allowed to be seeped in. It's been biologically treated. And other waste has been collected. Eventually, the plan is to set up an incinerator to burn it. But right now, we're collecting it and taking it back to Leh, which is a 4-hour drive away from where we are located. The terrain is not as green as what you're looking at right now. This year's there's been unusual amount of rainfall. It still remains to be one of the most driest places on Earth. But few weeks in the year, in fact, where the time of the year that we are in, it does get a little green. But more than the visual representation of where we are, the importance here is that Ladakh is an analog to ancient Mars. It has several features and supports extreme microbial life that helps us understand what Mars was like several billion years ago. And also the remoteness of it, and added to it the low oxygen and low atmospheric pressure and high UV radiation, makes it attractive also to the human spaceflight community. And that brings me to this slide, which is one of the main motivations for us to establish the station in partnership with the Indian Space Research Organization was that actually we wanted to help the upcoming missions. There's several missions planned along with them where we would be validating several technologies that ISRO is building, further understanding human health in extreme environment, and also refining mission protocols and operations. I'll rush through some of these. These are photographs taken when we had virtually inaugurated the station. We had the chairman of the Indian Space Research Organization who gave a short speech and acknowledged the effort of the team. And we had a virtual inauguration. We had a site visit. On the left, you see John Annalie and myself getting quite emotional, standing in front of the station a day before it was commissioned. And towards the end of it, we had visits from the Ladakh government officials, as well as a visit from the group director from ISRO as well. We also got the opportunity to interact with one of the 4 astronaut designates that ISRO has selected. And he was able to interact with our team and also give us a lot of useful feedback. On the top right, you see the 4 ISRO astronauts standing in front of the Indian Space Station mock-up. With that, I hand over to Annalie.
Thanks, Sid. I hope you can hear me clearly. Can you? Am
Yes.
I clear? Yes. Thanks very much, Sid and John. And good morning, everyone. I'm Annalie Beattie. I'm a director of Mars Society Australia. I'm an artist, and I've had some field experience in Ladakh. I've had 6 expeditions overall to the SOCAR site where Hope Station is, and 3 rotations to the US, to MDRS, including Mars 160. So today I'd just like to speak briefly about...
If you could speak a little louder, Annalie, you're still coming through a little low. Thank you.
What a shame. Okay, so today I'd just like to speak, how's that, briefly about one particular crew, the significance of one special MDRS crew for the building of Hope Station. So in February 2024, I led a primarily Indian national crew to the Mars Desert Research Station, and our team goal was to look at one station and plan to build another station in the high glacial deserts of Ladakh. So Mangal Yatri, which means Mars Explorers in Hindi, they were chosen because of their own research interests, but they're also chosen because of their ability to think about the future and learn from what they did at MDRS and take that knowledge, you know, to our station, our proposed station at that point in Ladakh. So what this means practically is, next slide, please, Sid. Yeah, thank you. And actually, the next slide, please, Sid. So what this means practically is that our science lead, crew geologist Bharti Sharma, compared the geology and the geomorphology of both the deserts in Utah and Ladakh to inform parallels on Mars. And she created a geomorphological map, and her work there, she led a whole crew to kind of always think in terms of looking at one thing through the lens of one thing to another. So our crew engineer in center, Rajvi Patel, focused on design materials and systems at MDRS, whether that meant power requirements or sizing of generators or solar panels or toilets or interior hab design. Manaz Jabin, a Ladakhi geospatial informatics person, just made it by the skin of her teeth to our crew with visa problems. And anyhow, she really studied what it might be like to set up an observatory in Ladakh in temperatures that sometimes might reach -30. So, you know, that was pretty great. And she was on the crew with us again this year. Our crew astronomer, next slide, please, Sid. Aditya Krishna, Karajiri, Madhad, Sudan, formulated comprehensive plans and strategies for the configuration of a telescope in Ladakh. Our crew biologist, Daniel Loy, tested baseline portable scientific equipment for to inform protocols and requirements for DNA analysis. And what this means is that anyone, including non-biologists with the right equipment, would be able to replicate these methods, including at the Ladakh Analog Station. Claire Fletcher in the centre conducted fieldwork at MDRS to better understand the protocols that we might need at the proposed Mars Analog Station in Ladakh, how to implement geoconservation practices from its inception as part of HOPE, ethos, values and protocols. As artist in residence at MDRS, my role was to think through drawing, to try and understand how we imprint on lands that aren't our own, and how by using art making as a methodology we can develop reciprocal responsibilities, something that can be translated to elsewhere, to Ladakh, and when we leave Earth to live on Mars. So at MDRS, we were driven by the science, and we looked at terrestrial things to understand more of the extraterrestrial. But it's important for us to say to you that the contribution of that crew at MDRS was brilliant and ongoing and invaluable. And this year, four of the 6 came to meet us in Ladakh. And so thanks so much, Mars Society, for your support. We couldn't have done it without you. And it just goes to show you, you know, what you can really do if you go to one place with a team goal and you think through the work that you're doing there, and then you'll be able to translate that when you go elsewhere. So thank you very much. I'll hand you back to James. Or Sid.
Actually, I'll just say one more thing, maybe very clearly, and maybe we weren't very clear in that. Hang on. if it wasn't for Robert Zubrin's timely support, belief in us, and um, contribution towards building of the station, this project would not be possible. And I only want to say this, that we actually started going into high gear in, I'd say, first week of May. And from there to actually having the first expedition kick off on the 1st of August, like just between that time, all the back and forth that James, others at the US Mars Society side, and Robert, despite his travels, that he was able to enable for us, and just the sheer excitement that I have thinking about the next season and all the work that can come in front of us. I'm just very grateful for that, and I really look forward to working and putting together a very strong program. We will be finalizing the program for next year and the website as well, that will allow researchers both within the Mars Society as well as outside to apply for it. And we look forward to working more closely together.
Thank you so much, Sid and John and Analia. We're also extremely excited about the Hope Station over here, and I think you'll have no shortage of interest for crew members and mission support resources. So thank you very much.
Great.
Okay, we have time for a couple of questions.
Okay, pardon the cultural ignorance of an American here, but what is the security and safety situation for volunteers that might be going to Kashmir?
Sure, I can take that one. So Ladakh is actually no longer part of Kashmir, and about 5 years ago, it was made a separate union territory. And what that has done is that all the travel restrictions that apply to Kashmir no longer apply to Ladakh. Ladakh's always been a peaceful region, originally part of the state of Jammu and Kashmir, and is now a separate union territory. Having said that, whenever we conduct our expeditions, we always start well in advance and collect. If you're traveling as part of our program, you would be receiving a form in which you provide to us all the information. And on behalf of each season's participants, we take the government approvals to travel into Ladakh. And some of these approvals are in excess, but we always go a little excess. We don't really leave it to the last minute and have to realize that you may or may not need that. Which is to say that somebody could travel into Ladakh as a tourist as well or as a visitor and not need these. But particularly when we are going in and doing research and collaborating with people, we want to make sure that we have all the right approvals in place. So that is responsibility that we take on as Protoplanet. We've been successful in the past, even before Protoplanet existed, to take that. We're on their files, and therefore it makes it a lot easier. So normally what happened is we would, once the program has been announced, people would submit an online form. We would collect all that information. You'd submit it. It takes about 2 to 3 months. And then what we would get in return is a government certificate that then allows the individual to apply for a e-visa, which is an e-conference visa in this case. It's all online. So it's fairly straightforward, but it does require that government letter. So that's all taken care of us. It's a process, but it's an understood process. We were able to successfully do that this year as well, despite skirmishes that took place in the month of May. The other last point I will make is that we are a fair distance, even though on the map it looks like we're on the borders. The location where we are at, it's in peaceful territory. It's at least I'd say 50 to 60 miles away from the international border. So you're in a secure zone, but it's areas that tourists and travelers and backpackers do have access to and can get to. So we've chosen locations based on those conditions.
Yeah, 50 miles does not sound far when you're in the US West or in Australia, but in the terrain of Ladakh, that's that's about half a day's to a day's travel.
Or that's a range of 6,000 meter mountains between you and and China, for example. Yeah.
You may have mentioned this briefly, but how do you guys at the outpost get water? Do you use reclamation? Do you pump it from the ground, or how does that work?
Thank you. That's a great question. Right now, we have a freshwater stream. So we normally drive up a small tanker to it, and using a pump, we fill the tanker and then we bring it over to the station and then we refill it. So we currently have a certain capacity that can support. Right now, it's I think 4 people for 10 days or something. I think we have a capacity of how much was it? Around 3 to 4 liters. Sorry, 3 to 4 thousand liters of water. But eventually, we will have the option to have a do boring and get access to groundwater. But we're being a bit careful about that. We're trying not to touch natural resources or the natural environment as much. So right now, that is the arrangement. We are still trying and understanding if we would need to get access to more water than that.
Congratulations on the launch this year. It's terrific. So a couple questions. What's your vision for the number of crews per year? And what's your vision for field EVAs? I noticed the fencing around the facility, which is understandable given the remoteness, but what's the kind of plan for field work and the number of crews a year?
John Hanley, you are right if I continue answering those?
Yes, sure.
Okay. So we are in the process of sending crews that are still doing some commissioning and refitting and rework of the station. We will eventually scale up the number of crews each year, but it continues to remain one of the challenging places where we can conduct analog expeditions, which is to say that we wouldn't want to fill up the calendar with tens of crews per year. It would still be a very high value, important, scientifically important, and very fragile ecosystem driven project. So right now, we are aiming to go up to about 4 crews per year, 4 to 5 crews per year. And then depending on the demand for it or other feedback, we would be happy to consider maybe expanding the station or finding ways in which we can set up the infrastructure to support more people. As far as EVAs are concerned, the fence around is expandable. It's essentially owned by it's a piece of land that is owned by a native of that place, but it also sits within national park territory. So it's kind of a shared resource between the people who live there and the government. And we normally comply with both those groups and we work closely with them, which allows us to therefore do EVAs much beyond where we sit. So we will have, access to, I'd say, in miles, probably 30 to 40 miles diameter around us easily that we are able to actually get to. So that's not a problem. Conducting long duration EVAs is possible. We are about 5 miles south of the Sokar Lake, and there's several regions of interest that we've already identified in that area. So there's an elaborate plan to conduct EVA training in the near future.
Okay, we're going to leave it there. Thank you so much and congratulations again.
All right.
Thank you, James.
Thank you.
I just make a remark.
Oh, sure.
So just to answer that implied here and other people may be wondering about. So we partnered on this project with these other organizations, as you can see. And the basic deal is after this preliminary activity.
It's angle.
It's channel conflict. Okay. So there's going to be a little more preliminary stuff, but once this thing gets going, we're going to be able to choose half the crews. That's what it's going to be. And so probably, as he said, initially be order of 4 crews a year, of which we'll get 2. And then I think eventually it will grow to about 8 crews a year. So that's what it's going to be. So there'll be calls for volunteers for crews to the Hope Station. May take a little while. I mean, next year might still be a lot of building up kind of stuff, and maybe only 1 crew on our part. But this is where this is going.
Thank you. Okay, awesome. Thank you so much, everyone.
Thank you very much.
Thank you. Thanks, James. Thanks, Robert.
See you.
Hope you guys have a
Thank you,
great
Robert.
last day to the convention.
Thank you.
Thanks, Robert. Thanks, James.
Okay, our next speaker is Dr. Abigail Freeman, the Deputy Project Scientist of the Perseverance mission. Welcome to the Mars Society. Come on up.
Wonderful, thank you. Great, thank you so much for inviting me to come speak to you all. I'm really excited to be here. I realized I didn't finish writing the title. I'm actually the Deputy Project Scientist for Curiosity, which is a very similar looking rover. But today I will be talking to you about the Mars Curiosity rover and just showing you some of the things that we've seen looking at Mars over the last 13 years. I have to start off with what we saw yesterday morning when we came into work and we all had to plan what to do over the weekend. This is where Curiosity is currently parked. We're looking at some really interesting rocks that we're calling the boxwork structures. And let's see if I can pull up a laser pointer here. They boxwork structures, and we call them that because they look like kind of boxes. And it's this series of ridges and hollows that we're investigating, trying to understand what were the processes that formed these different ridges and hollows. We think groundwater was probably involved, and we're wondering, was it a process where water came up and formed some sort of cement in here? What was the kind of water that was involved? Was it really salty? What was the temperature? Was it something that was long-lived? Did it happen very quickly? How did that affect the rocks? And so we've been having just a wonderful time exploring these really enigmatic features. At the moment, we're looking for a place to hopefully drill, collect some rock samples to put into the onboard laboratories on Curiosity. And so we planned a little bit of a bump into one of these hollows that we'll be doing over the weekend. And when we come in on Monday, hopefully there'll be a piece of rock. There's very few rocks in the hollows, but there's one little one right over there. So hoping something like that will be in front of the rover, and we're going to set us up and hopefully drill next week or the week after to figure out what they're made of. But before I get too far, let me jump back and show another image from Curiosity. And this, of course, was the image that we saw over 13 years ago when the rover landed at a site called Gale Crater. It's a bit messy in this image. What this actually is an image from the HAZ cam on the rover. That's the camera underneath the belly of the rover that we use to see hazards as we drive. And when we landed, we kicked up a whole bunch of dust and rock that got on top of the lens. And so good thing we built in a dust cover, flipped that dust cover off, and this was the view from landing 13 years ago. Couple things that you should notice, of course, the shadow of the rover, I think, just looks really cool. But really importantly, in the distance was our target of exploration. This is a mountain named Mount Sharp. It is 3 miles tall, or 5 kilometers tall, if you like metric. And this is what Mount Sharp looks like from orbit. It is in a giant crater called Gale Crater. That's about 150 kilometers across. It's right on the equator of Mars and what we call the hemispheric dichotomy between the ancient southern highlands and the slightly younger northern lowlands. And what's really remarkable is this mountain in the center of the crater. The mountain is actually composed of a bunch of sedimentary rock that were brought into the crater and filled the crater up. And the goal of the mission was to be able to land at the base of this mountain and read these sedimentary rock layers as we climbed higher and higher. And by doing so, it's like reading a strip chart of Martian history. Kind of like if you were to go to the bottom of the Grand Canyon and then hike your way up, you'd be seeing many years of Earth's history and the different processes that were going on that formed those layers. And so we wanted to understand what those processes were and what that tells us about the history and the habitability of Mars. So that's what we've been doing for the last 13 years, is climbing this mountain. This is another view of Mount Sharp, again from our landing location, but this is now taken with our color mass camera on top of the rover. Obviously, you can now see the mountain in the distance, some other cool things to see. I love this image because it shows how we landed on Mars using the sky crane system, which is this kind of inverted jetpack that lowered us to the system. And these are the impingement plumes of where we had the thrusters interacting with the surface. When we started driving, you know, the wheel tracks just started like they came out of nowhere. So I love thinking about that. But if you zoom in, this is really the first look with our telephoto 100mm lens on our mass camera. And it's remarkable that you can see the layers and layers and layers that we saw from orbit. And here we're starting to see them now from the ground and resolve them even more closely. Besides just having layers, we could tell from orbit that the layers were made of different compositions, which was another clue that we'd be able to see this really dynamic history of Mars as we climbed our way up through them. And so I've labeled some of them here. Of course, the cratered plains that we landed on top of. There was a big dune field right at the base of the mountain that we actually had to spend about 2 years skirting around before we actually got to the base of Mount Sharp. And then moving higher up, there's a unit with a mineral called hematite, which is an iron oxide that usually forms in the presence of water. There was a clay-bearing unit, which we could see from orbit. We could map that there were clay minerals associated with these rocks. Those are usually minerals that form in water and usually kind of pH neutral water. And then moving even higher up, we could see the kind of butte and mesa forming layers. This is a sulfate bearing unit, or a salty unit. And we're seeing this transition now from clay minerals to salty minerals. And I'm going to talk a little bit more about that in a few slides, but it's an important potential transition in the history of Mars climate. We're now all the way here-ish, so we've been making our way up, reading all these layers. We're deep into the salty unit now, investigating those boxwork structures all the way over here. Another remarkable thing about this mound is that we can estimate how old it is, and in addition to the minerals that we see, we can also see that it should have formed at about the time that we think Mars was undergoing this dramatic climate change. So 4.5 billion years ago, we don't totally know what Martian climate was like. We think there was at least more water on the surface. And then, of course, now today, we know Mars is very, very dry and cold. And then we know there was something really interesting that happened about 3.5 billion years ago that caused Mars's climate to go through some big changes. And so by going to this particular strip recorder of Martian history in this section, we were able to see, you know, what were the environments that were associated with these climate changes and how did that affect the potential habitability of the planet. Curiosity itself is our kind of Mini Cooper-sized rover. It has 10 scientific instruments that are designed to interrogate the geology and the environment of the area at Mount Sharp. I'll just point out a couple of the really, I mean, they're all really important ones, but the ones that drove the rover to be as big as it is are these 2 laboratories we have on board. That's why we call Curiosity. It's also the Mars Science Laboratory. It really is a mobile chemical laboratory that we have on the surface of Mars that is able to measure the composition of the rocks, understand their definitive mineralogy, what minerals are there, the crystal structures that are there. That's the instrument called ChemIn. And then there's also an instrument called SAM, which is able to detect volatile compounds in the rocks, things like water, things like carbon-bearing organic molecules, and make measurements of things like the isotopic composition of the rocks and the atmosphere as well. To get rocks into these laboratories, we need, of course, a drill that will drill into the rocks, create a powdered rock sample. That's what we're going to be doing hopefully next week, is getting more information about the composition of these rocks. This is Curiosity's journey. Yesterday, we planned sols 4,686 to 4,689. This audience is probably familiar, but a sol is a Martian day, a little bit longer than an Earth day. We have driven over 36 kilometers, so If you do miles, it's a little over 22 miles. The really important statistic for this particular mission is how far in elevation we've climbed, how high up the mountain we are, and that's over 900 meters in elevation. So we've made quite a ways up to the top of this mountain, although for the 5 kilometer tall mountain, we have quite a ways to go to get to the top. But starting off, I'll just show you a couple pictures, of almost ancient history at this point about what it was like when we landed in an area called Bradbury Landing and then made our way actually in the opposite direction of Mount Sharp to a location called Yellowknife Bay, which was a specific location we could see from orbit. We thought if there ever was a lake here that was bringing in sediments and building up the lower part of the mound, that's where the lake would be. And so we drove there, and this is the beautiful site that we saw. And what we found back on Sol 166 of the mission, or back in January 2013, was indeed these rocks had all the characteristics of being lake deposits. They were very fine-grained. They had clay minerals in them, which is what you might expect to be deposited in a lake. And super importantly, one of the things that we found were the presence of carbon-bearing molecules, organic molecules that were trapped and preserved in this lake. And that was something that we found relatively early on. Although 13 years later, we're still making discoveries from the samples that we collected here. Because we have these wonderful onboard chemical laboratories, we're able to work with them and make experiments and change parameters in the way that we analyze samples. And we knew this site was really important. And so what we actually did was we called it doggy bagging the samples, where we stored some of the samples in the reaction cups in the instrument to save for future analysis. We were able to go back to our laboratories on Earth. We were able to tune how we run experiments on the rover, how we measure the chemicals in here. And a few years ago, did another experiment with the samples, and what we found increased our knowledge of the kinds of organic materials that were here. So this is the only slide I have with words, but just going through, this was a result that came out earlier this year, and I think it's remarkable that we're having kind of top 10 mission results coming out now from samples that we collected 13, 12 years ago. But what we found preserved in these lacustrine mudstones was not only just simple organic molecules, which is what we first reported, but we also started to find more and more complex organic molecules, bigger and bigger molecules. And what was recently reported was present in these, or actually these long-chain hydrocarbon molecules, which are basically anything with carbon and hydrogen. And these are some of the biggest and the most complex organic molecules that we found on Mars to date. And we don't know what made these molecules, whether it was biology or they were delivered from outer space or they were part of the interior composition of Mars. But what is remarkable is that this shows us that Mars has the ability to preserve these potentially important evidence of life, or the building blocks of life, in its rock record, even in rocks that are billions of years old. They haven't been destroyed by the radiation and the really harsh environments on Mars. So when we're thinking about the search for life on Mars, we can be excited about the fact that there may still be these evidence and all of this information still present in the rock records. I just love this picture. This is our current collection of drilled samples. There's actually 43 drilled samples, but 42 makes a better grid, so that's what I'm showing here. But these are all 42 of the drilled samples that we've collected over the last 13 years of the mission. This is remarkable because it shows you just how diverse Mars is. It's not just the red planet, but when you drill beneath the surface and you look beneath, you see Mars is the green planet and the gray planet and the purple planet and the brown planet. And all of these different colors are related to the different compositions of the rocks, which is related to their unique history, how they were in place, and then what happened to them in the billions of years after they became rock. But I'm going to move on now and just talk about kind of what we've been doing in the last 5 years or so. We made our way up most of the mountain. We found a lot more information about the presence of lakes that were filling this crater, and then also a really complex history of groundwater that then came in after the lakes. But I'm going to move all the way up, and I'm going to bring back that idea about this transition from clay lake minerals to salty salts called sulfates. And this is an area we explored back in March 2021. We started our exploration back then on Sol 3048, called the clay sulfate transition. And this is a particularly awesome image because I think it shows the transition really clearly. We could see it from orbit, but it was super obvious from the ground too. So all of these tan rocks in the foreground, this is really the top of what we call the clay-bearing rock section. And then moving up here, this is where we start to see the sulfate unit, these salty rocks. And you can see not only do they have a very different composition, but they have a very different expression of how the rocks look. And so a big question that we wanted to understand was why? What caused this change? What kind of environments did it reflect in Mars? Was this a one-time thing? Like, did the lakes disappear and then Mars just became really dry and salty? Was this something that was a more punctuated event? And so by exploring these rocks over the last 4 years, we've been able to answer that question. But before I get into that, this was just a nice image to bring up another point here. So this feature here, it's just a very photogenic mountain. We called it Mont Mercou. We were in an area where we were naming all of the rocks after the Nontron region of France, which is the type locality for a clay called nontronite, which is the kind of clay we found in the clay-bearing unit. But if you take a look at this beautiful Mont Mercou, this is another image we took when we were parked at the base of the cliff, looking at what all the rock layers were telling us about how it formed. But this is an image we took right after sunset in the wintertime. And this represents another amazing discovery of curiosity, and something I don't want to forget as I talk about the rocks. The rover has also been making these measurements of the Martian environment for the last 13 Earth years, or as of, it was 1 a.m. UT on Monday, we just passed our 7 full Mars years mark. So we now have a record of 7 Mars years of climatology that we've collected with Curiosity. It's the longest climatology record. The only mission that's lived longer on the surface was the Opportunity rover. But with Curiosity, what we've done for the last 7 Mars years is collected a nearly continuous record of the temperature, the pressure, and the relative humidity every hour with our REMS instrument. And so it's this wonderful, complete picture that we're learning all about the Martian environment. We made discoveries like these clouds that come out during a certain time of year, these noctilucent clouds. They're made of CO2. We were able to look at the colors of the clouds to understand the grain sizes and how they formed. And I think this is just a beautiful picture, because when I think about going to Mars, this is a place I could see myself setting up my tents and just lying out, looking up at these beautiful clouds being lit by the sun because they're so high up, even after the sun has set. This is just another awesome cloud picture. We took this one, the last noctilucent cloud season, back in February 23. These are these crepuscular rays, which are like these God rays, you might call them. If you're a photographer, this makes awesome photographs, and just so cool to the first time see this happening on Mars. To me, images like this really make it feel like a place, because it are these kind of Earth-like phenomenon that I really relate to. But let's go back to the sulfate unit. This is an image as we made our way up. This is an area called Paraitapui Pass. This was now when we were naming rocks after the Roraima area, where these really cool buttes called tapuis in Brazil. And this is just a wonderful example of the way the topography has changed, how we're seeing these giant buttes that are now towering above the rover. They made it tricky for us to work out our comm. It turns out if you're parked next to a giant mound of rock, it can sometimes be hard to see the orbiters passing overhead, that you need to relay your data. So we had to be very careful as we planned our path. But they were great for geologists, because they give us this amazing view of kind of the strip chart of the layers and really help us understand the structures. And what we were able to find out is that most of these rocks have structures that are indicative of being deposited in a wind-blown, sandy environment. So things like dunes and sand sheets and ripples, those are all the kinds of structures that we were seeing. So this is telling us that, yes, Mars is having this drying out period, the lakes are going away, but what about the salts? This was a cool thing that we found as we were driving up through. We also started to see some really interesting, they're called diagenetic features, features that formed in the rock, usually by groundwater. The blueberries that Opportunity found that are so famous are another example. But here we're seeing these kind of golf ball sized kind of nodules in the rock, and they were really dramatic, really interesting. And because we're on a 1-ton rover, we were able to actually drive over them and crush them open and make measurements of their chemistry. And what we found was that these nodules were the carrier of some of the salts that we saw from orbit. So that was a really interesting finding, and something that you really need to be on the ground to be able to figure out. We're going to keep moving our way up the mound now, and I'm going to take this box that's shown in black and just zoom in here and give you a slightly different perspective just because it's easier to show all the details. Here again is the bottom of the clay-bearing unit as we make our way up through to the magnesium sulfate-bearing unit. That Parai Takui pass that I showed was this area right here. And this is just another image I'll show. We were parked about here looking right up the mountain. And this was the view we got. And this was one of the first view we got of a channel that we were about to drive up. And this is just another amazing picture we took back in November 2022. It's one of my favorite images of the mission. I have it printed out really big in the hallway across from my office. But it just shows all these amazing layers and layers and layers of history that we're going to be able to access on Mount Sharp. And then even higher up, really cool parts of the way tippy top of the mountain that are formed in a totally different way that we don't know anything about at this point. But as we made our way up, we made our way to this really interesting layer called the marker band, which is this kind of dark layer that you can trace all the way around Mount Sharp. We had no clue what it was from orbit. Was it an ash layer? Was it something different? This is what the marker band looked like when we got here. It kind of looks like a Pahoehoe lava flow like you might find in Hawaii, but it wasn't. It turns out this is also sedimentary rock, but what is making all of these structures are these ripple features. And they're these symmetric ripples, and when you get on top of it, this is what it looks like. And every single geologist on the team immediately agreed what this was, which is super rare. But what it turns out this is something called wave ripples that formed in a rather shallow body of water, probably just a couple feet deep, as it sloshes back and forth. So kind of like you might find on the shoreline of a lake or if you go to the beach. And this is exactly what we saw here. So this is exciting because it told us that even though we had been in this pretty dry environment, all of a sudden liquid water was back on the surface. And this is some of the best examples that we have in the entire mission of an ice-free lake that interacted with the surface. So what we found is Mars dried up, but it wasn't this sudden dry up. It's this kind of pulse. It gets wet and then dry and then wet and then dry. And so there's a lot of dynamic climate change that was happening in this period of Martian history. Another example of climate change we could see as we came up was this Geddes Vallis channel and Geddes Vallis ridge. This is just a kind of zoom in of what the ridge looks like. It's this big channel that cuts down through a lot of Mount Sharp. Here's curiosity for scale, by the way. It's this massive, massive pile of rocks. We didn't know what formed it. Was it a dry, just a rock fall that came down the mountain? Was it a river that transported these rocks? Was it kind of a slushy debris flow? We were able to get up to the base of the ridge and see, for the first time in a long time, this big contrast. Instead of all of these rocks that were all kind of tan and the same, now we're starting to see a diversity of all different kinds of rocks being brought down from higher on the mountain, all of these black rocks with different textures and sizes. And as we made our way up the ridge and towards the channel part of the ridge, we were able to look at all the diversity and types of rocks. And we actually concluded that, yes, water was involved in bringing some of these down the mountain. And it wasn't just one episode. It was hundreds or thousands of different pulses of water that came. And this would have been something that was one of the last things to happen in the entire history of Mount Sharp, because it cross-cuts. It lies on top of all of these other rocks. This is a traverse making our way up this sinuous channel. And this is what it looked like when we actually got into the channel. It's a bit of a busy image, so I'll add some labels here. Here's kind of looking downhill towards that giant ridge that's way bigger than the rover. Here is some of the debris that filled the channel. This is our usual salty unit rocks here. And then something caught our eye as we were actually crossing over the channel were these really weird looking white rocks that didn't look anything like we'd seen before. Here's another view of us as we drove down into the channel. You can see these are little patches that we've brushed off with the brush on the end of the rover's arm. But here are these really bizarre white rocks, very distinctive and unlike anything we'd seen before. When we took a closer look at them with our hand lens imager, this is what they look like, a very distinct texture that hopefully you can tell from all those other images I've been showing you. And of course, we're a one-ton rover. We like to break things up to understand what they are. So we drove over one of them. And when we broke it open, we were able to see that the inside was kind of this yellowish material. And when we put our instrument arm actually down on them and were able to assess their composition, we found their composition was pure elemental sulfur. which was, I came in that morning and it was like, what? Wait, no, you mean sulfates, which is something we see all over Mars. And it's, no, this is sulfur. And it was like, wait, that was not on my bingo card. What? So really unexpected finding. This is the only time we found elemental sulfur on Mars. On Earth, you can find sulfur that forms in places like hot spring deposits. A lot of the time, microbes are involved in its formation. We're not in a hot spring deposit here. At least we've seen no other evidence for any high temperature minerals. So we are scratching our heads about how this formed. We have some ideas that are going through peer review right now, but it's a really exciting discovery. Not totally sure what to make of it at this time. But just goes to show you, even 12, 13 years into the mission, we're still discovering one of a kind, first ever seen things on Mars. This is just, let's see if it plays, a video that we took. This is as we went into a period called conjunction, when Mars went behind the sun and we can't command the rover. We just let our cameras take some images, and this is a day on Mars as the shadows pass over the sky. I just really like that video. But here is now wrapping back to where we are today at these boxwork structures. This is what they look like from orbit. Again, these kind of big boxes, giant decameter scale fractures that probably formed as groundwater came up 900 meters up the side of the mountain, which is just wild to think about. How did you get groundwater coming up so high to form these resistant ridges and hollows? As we were making our way, this is I'm just showing a bunch of pictures now, a high-rise picture that caught us mid-drive, but wrapping up, showing our approach to these boxwork structures. This is a late afternoon image, so with the low angle sunlight, you can start to see the relief of them in the distance. And then, of course, this is where we are today. This is now a color picture. Heading down into one of these hollows right here, this little block, to see if we can drill it. Hopefully we can, to understand its composition. And then we'll hop back up onto one of these ridges and drill that and have a really nice paired sample. So I'll just end with a teaser for the road ahead. We're going to continue climbing Mount Sharp. This is a view into the top of the mountain. This is what we call the Yardane unit. These are really enigmatic. We don't know what these rocks are made of. We don't know how they formed. They might be reflective of a whole regional unit that's called the Medusa Fossae Formation that we see other places on Mars, and is also super enigmatic. So I'm super excited to keep roving and get there hopefully one day and figure out what this tells us about an even earlier part in Martian history. And I'll end with our beautiful postcard that we took just a couple weeks ago with our tracks in the distance as we made our way across the boxworks. So thank you very much.
So Abigail, not to be argumentative, but to
Sure.
use things up for the morning. I mean, for 25 years, some of us have been trying to get Martian exploration to do real astrobiology, not the pseudo-astrobiology that gets through peer review. And part of that has to do with looking for extant life. And now we have the fatty acids that are found, right? You're found in a place where they're not expected, but they're not expected primarily because NASA's view of Mars has been poisoned by the misinterpretations of the GC mass spec experiment 50 years ago. So, Milan et al., when they found benzoic acid in the Bagnall Dunes, didn't bother to look at that sample for a couple years or something. You know the story better than I do. But the bottom line is that let's just say there is extant life in some of that soil over there. Can we now, this is the question that Robert asked yesterday, can we now go back and repurpose the instruments? We have a good idea of what the metabolism of that life would be. We have a good idea of what agnostic biosignatures we can look for. Is it possible at this late date with the instrument payload that you have to actually go look for extant life in these soils as opposed to doing what is basically a geological survey, but do actually a real astrobiology survey? But I've thrown the bomb, so I'll let you respond.
Yeah, and let me preface that I am not an organic geochemist. So, let me tell you what I've been told by the people in the field who are experts. It is my understanding that we're pushing this instrument to the limits of what it can do in terms of its detectability. I think what we've managed to do has been remarkable, how we've been able to change the way we analyze samples. For example, one of the things that we did with this recent discovery is understanding the perchlorate problem, right? When we first analyzed the samples, the perchlorates were there, destroyed everything. So we figured out a way to do the step heating experiment where we would get rid of the perchlorates, but not go all the way. And then we would be able to analyze kind of those higher temperature materials that were coming up without them being destroyed. And so we've been able to tune those knobs to pull what we could out of this wonderful laboratory instrument. And I think it's remarkable. I think in terms of directly finding life, you know, we talk about all of the different things that we would need to look for. I think there's other lines of evidence that we would need to find that we don't have the capability yet with this rover. Maybe Perseverance is on the edge with things like Pixel and Sherlock to be able to do these fine scale measurements and to be able to get these coordinated data sets. So no, not with Curiosity. I don't think that's possible, but I think what we've been able to do is still been extraordinary in how we've been able to MacGyver the instrument. Very proud of the team for what they've done.
So thanks for the talk. This is really fascinating stuff. I have two questions. One's just real quick about you know, your look ahead plan. Is there any potential that we might try to actually get to the summit of Mount Sharp?
Yeah, that would be really fun. Just to say we've climbed it, but no, I don't think that's realistic given how high the mountain actually is. And when we can project out how long we think our power supply is going to last, it's just going to be too long. That said, we think the whole kind of upper half third of the mountain is probably very similar material. So as long as we can get a taste of that material, it's going to tell us a lot, and there'd probably be diminishing returns if we just tried to continue to make our way up through it.
Very cool. And the second just follow-up question to similar to what was just talked about with the previous question with these larger hydrocarbons that were detected. Again, I think this might be a little bit out of your wheelhouse, as you said, but with the organic chemistry, I'm curious if you've heard any experts in there, if they've said, you know, just dream scenario, if we had like a particular protein or certain types of amino acids that would be like this smoking gun or something like that, if I could just plant something there that we know we could detect, if you've heard anything like that, that could be, you know.
You know, and this might be a good question. I don't know if she's involved for our next speaker, because I know the MEPAG, the Mars Exploration Group, is putting together actually a special group that's looking exactly at this kind of question about the Mars Life Finder mission. Is there a specific mission we could send to Mars to make an example in situ that could tell us something more that would kind of push the needle more for the search for life? I mean, I think the best way is to bring back some of the samples that we have collected now.
Have you looked at the oxidation reduction potential to explain the S0, the you know, the unoxidized, unreduced sulfur you found in the so-called leopard spots? If you look at it from the standpoint of condensed matter, you might begin to see that there's more answers there from the standpoint of condensed matter, because there's an electrical circuit that connects the heliosphere to the surface of Mars in certain events.
You know, I haven't heard of that. I will say, as geologists, we think about how things work on Earth and what we know on Earth. The sulfur here, this isn't related to the leopard spots at all. Different rover, other side of the planet. But yeah, so the sulfur here, but it is, so sulfur as it comes out of the Earth, or presumably out of Mars, is in its reduced form. On the Martian surface, when it sits around, it gets very oxidized, and that's where we see sulfate everywhere. So how did this go from sulfide as it came out to sulfur precipitate? Did it go to sulfate? Was it reduced? You know, we're looking at all these different aqueous geochemical pathways that could have gotten it there and trying to figure out what may have happened.
Suggested this to Steve Squires and John Grotzinger a few years ago, and hopefully you would get there about the condensed matter outlook. Good point.
One last question, Robert.
Okay, I have just a little question and then the main question.
Okay.
Okay. The little question is, have we observed any phosphorescence on Mars? But the other, the more interesting question is, in this conference and in recent news articles, there's been all these little bits of the causing suspicion of life on Mars. I mean, you just showed a chart with oil discovered on Mars. Okay, with the you know, the high chain paraffins, and then there's this business with the sulfur, and there's this business with the whatever they were, iron phosphates, and you know, there's all these little things that are all like, well, if we found this on Earth, it would have been life. If we found it, you know, and it's like starting to accumulate. And I'm wondering, you know, if the team could put together, not a review article, because only scientists review articles, but more like a Scientific American kind of article, where this stuff is assembled of, the reasons, to suspect, not prove, but you've got a suspect here. You can bring this in front of a grand jury. No, really, to the existence of life. And then I think the question that Steve brought up is kind of relevant. Is if you say, okay, we've got now reasons to investigate this suspect, how could we redirect the activity of curiosity and perseverance to say, okay, if this hypothesis is true, what else would we find? Okay, if this hypothesis is true, what else would we find? And go look for that and put this to the test.
Okay, let me take that in two parts. So you asked about phosphorescence on Mars. I'll point you again to Perseverance, the leopard spot, the phosphate, iron phosphates, I think is going to be in your Perseverance data. With Curiosity, I don't think we've found any phosphates, or if we have, they've been very trace amounts. Your question about, I agree. I think in the last 5 years, there have been a number of very tantalizing discoveries that have continued to move the needle to Mars being an intriguing place when you think about the search for life. I think the long-chain hydrocarbons, which are not oil, but they are hydrocarbons, is intriguing. I think that there was a paper about heavy isotopes that was intriguing. And then the recent Perseverance leopard spots. We're finding all of these intriguing, tantalizing hints. With the vehicles that we have currently on the surface of Mars, there is nothing that we can do, I think, to go beyond. I think we have pushed these wonderfully complex machines to the limit that they are able to analyze. We have thrown everything we can with the payload that we have. I think it's a wonderful argument for the continued surface exploration of Mars. I think there's still a whole lot more we have to learn. The story is continuing to get more and more interesting the longer we look.
Thank you very much. Excellent presentation. Hi, Dr. Hamilton. Can you hear me? You are on mute.
Yes, I can. Can you hear me and see me?
Hello.
Good morning.
Let's do a quick sound check.
Can you hear me talking?
You sound great. We can see you and hear you. Do you have any slides to present?
I do, in fact. Let me share those with you right now.
Excellent.
All right.
Okay, our next speaker is Dr. Victoria Hamilton. She's the chair of the MEPAG, the Mars Exploration Program Analysis Group. Welcome to the conference, Dr. Hamilton.
Thank you very much. Thank you for having me. I'm very sorry that I can't be there with everybody in person today. Unfortunately, I had a pre-existing travel commitment earlier this week and just got back last night. But I really am excited to talk to you about the future of Mars exploration. I'm hoping that Abby just gave you some really great eye candy and talked a lot about the science of Mars. What I want to talk about today is the future of Mars exploration. And so I will go over very briefly the fleet of robotic missions at Mars that are currently underway and have been going on, some of the ones that are no longer active, and how they fit into an overall program of Mars exploration. I want to spend a little bit of time talking about the development of priorities, because how we develop our priorities is something that I think a lot of people maybe don't have very much insight into, and yet I think it's a really important part of understanding both where we've been and where we're going. And so from that, I will lead into talking about NASA's current Mars future plan, what the next decade or two of Mars exploration looks like. And then I'll transition over to applications of nuclear technology to Mars exploration, based on a singular event that I attended, but an example of how Mars science is starting to be integrated into those kinds of conversations. I will give you a disgracefully short one-slide overview of the Moon to Mars program. That program, understandably, has been largely focused on Artemis and lunar science right now, but we're moving into the early stages of additional Mars expansion in that, and so we'll talk a little bit about where you can find more information about that. And then finally, I'll conclude with the budgetary outlook for Mars exploration going forward. But I wanted to start out with an overall sort of thought about Mars exploration, which is that the evolution of our robotic capability has really dramatically changed the human understanding of Mars as a planet, but Mars as a planet within a solar system, and the impact that the data we get from Mars has on our broader understanding, especially because it can give us information about periods of time that are no longer really accessible to us on Earth in an unaltered kind of state. So the next phases of that will be sample return and human exploration, and they will undoubtedly be step functions in our understanding. So here's a fleet chart of NASA missions and some of our international colleagues' missions to Mars in the last 20 some odd years. And what you'll see is that there's a whole suite of landed missions, rover missions, orbital missions that all complement each other. And Mars exploration as a program has been so successful because it takes what we learn from early missions and takes that and adapts it and builds upon it and complements it with the subsequent missions. And so you can see kind of what we've been doing in the last 20 some odd years and where we hope to be going in the immediate future. But I think what I'm talking about here is really well graphically represented in part by the arrows at the bottom of the figure. So back in the very late 90s, early 2000s, we learned that there was in fact water on Mars, in Mars, beyond its presence at the polar caps. And so that led us to many missions and instruments and investigations focusing on where that water is. And that, of course, leads us into the idea of habitability and where are habitable locations on the planet Mars. And then that, of course, brings you to the question of, well, who was maybe habiting it? Is there evidence of fossil life on Mars? And now coming into the next several years and decades, probably, of exploration, we'll be looking for actual signs of extant life, not just fossil life. And of course, interwoven throughout all of that is how Mars exploration feeds forward into the preparation for human exploration. So let me spend a little while talking about the development of priorities for Mars exploration. NASA, of course, has its own internal processes, and that's something that you should hear about from someone at NASA. What I'd like to talk about are some of the non-NASA sources of information, and I'll focus on two of those today. The first one is the Mars Exploration Program Analysis Group, MEPAG, of which I am currently the chair. This is a volunteer organization that supports the Mars Exploration Program in a variety of ways. We host meetings. We're a volunteer organization of members of the community, scientists, engineers, and other interested people. We're open to anyone in the world who wants to participate. We will provide input to NASA via topical reports. We also maintain a document called the Goals Document. This is a living document that outlines the objectives or the goals and objectives and investigations that the science community believes are the top priorities for Mars exploration in the robotic program going forward. We'll talk about the fact that human exploration in that document is also increasingly integrated into that science, both the science that is enabled by human explorers as well as the science that can be conducted and conducted better in many cases by human explorers. Something important to understand about MEPAG is that we are generally not tasked with specifically taking into consideration detailed budget profiles when we do our work, and we are not an advisory committee. The other large source of information from the outside going into NASA on Mars exploration is the national academies. And they have two different primary mechanisms for producing that information. The first are ad hoc committees that are requested by NASA. And they usually have a very specific statement of task, questions that NASA would like to have answers to. Oftentimes that can include summaries of the state of the field or the technology or whatever it may be. And so those reports can cover science topics, they can cover technology, they can cover things like programmatic issues or policy. Those committees are generally comprised of members of the community, science and engineering communities, others as appropriate, including members of the national academies. The other major source of input to our priorities are what are called the decadal surveys. And the decadal surveys are performed for each of the major divisions within the Science Mission Directorate of NASA. So planetary science is the one of relevance to Mars, but there's also decadal surveys for things like earth science, astrophysics, heliophysics, biological and physical sciences, and so on. These decadal surveys are conducted by congressional mandate, and NASA sends the requests to the academies to conduct these studies. They too are primarily comprised of scientists and engineers and other subject matter experts on various topics relevant to the robotic exploration of our solar system. This group, in fact, is tasked with undertaking detailed consideration of likely future budgets and making sure that different missions and different activities are phased through time in such a way that they can be conducted within the budgets that are anticipated. And then the other thing these documents do of fundamental importance for NASA is make actual recommendations about scientific priorities and flight mission priorities. And because these reports are congressionally mandated, Congress expects NASA to follow these decadal surveys to the best of their ability and execute them as designed. So in the latest decadal survey, which was released in 2023, the highest scientific priority for the robotic exploration in planetary science was Mars sample return. And this is not the first time that this has been the top priority of a decadal survey. It was the top priority of the previous decadal survey, and it was the top priority for Mars in the decadal survey prior to that. So this is a long-standing community priority to get samples back from Mars. And this prioritization really does reflect how important we believe these samples will be to enhancing our understanding of Mars and as an object within our solar system. Beyond that, it also will provide substantial information for planning for human spaceflight missions and human explorers, not just in terms of the science that they might do as follow-on science, but also to help development of things like spaceflight systems, everything from HABs and landing systems to, understanding the dust, not just as a particulate that will get into everything, but its chemical reactivity and, issues of health and human safety that will be informed by understanding what is really there on the surface in a way that we can't from robotic missions. The Decadal Committee, beyond that, also fully supported the continuation of the Mars exploration program as a program, precisely because it does allow for a very strategic approach to Mars exploration. The other mission that was prioritized for Mars was a concept called Mars Life Explorer, which was an extant life detection mission. This would be a medium-class Mars mission, which in the decadal definition is a mission on the order of $1 billion, $1.5 billion or more, whereas flagship missions such as Mars sample return are usually in the several billions of dollars and up. So I wanted to talk a little bit about technology priorities identified in the Decadal Survey. The technology chapter of the Decadal talks both about short-term and very long-term advances that we should be looking towards in furthering our exploration of Mars. And that longer term time frame goes as much as 20 to 40 years beyond the term of the decadal itself. And it includes a wide variety of topics. It's not very restrictive in that sense, but most of the technology developments in one way or another are aimed at reducing mass, power, volume needs for instruments and flight systems. That not only helps keep cost in check, but it also helps us with development time. And as a result of all of that, making sure that we can be as productive as we can possibly be when we do get there and perform at our best capability. And that involves maturing a lot of technologies to be ready to fly on a spaceflight system. In terms of the priorities the decadal identified, they were focused very much, of course, on general scientific instrumentation, in particular those aimed at life detection, especially with that mission priority in mind. But there are a lot of other technologies that could benefit from technological development, such as more complicated sample handling than we can currently conduct, the ability to operate in extreme environments, both hot and cold, understanding and developing better communication systems that allow us to transmit more data and do more science as a result. All kinds of issues around mobility, whether that's entry, descent, and landing, or mobility once you're at Mars. Issues, of course, around planetary protection, RTGs, power systems, and subsurface access. They also identified disruptive technologies that these would provide, again, step functions in our capabilities now, not just in our knowledge. And so those are things like increasing use of commercial launch systems, quantum computing, and AI and machine learning. We'll talk in a moment a little bit about the nuclear thermal propulsion and electric propulsion that could really change how we get to places and how quickly we can do that. Commercial exploration as an endeavor where NASA is not the only one flying things to other destinations to do science. So an example of that is the commercial lunar payload services and the potential for something like that to be started at Mars in the near future. And of course, in situ resource utilization has long been an area of technological interest and continues to be and will be for the foreseeable future. So with all of that external input in mind, plus NASA's own strategy documents, they have developed what we colloquially refer to as the Mars Future Plan. And that document covers the period from 2024 to 2044. And it was released in December of last year. It covers 3 specific science themes. First of all, exploring the potential for Martian life, supporting the human exploration of Mars as that becomes closer to becoming a reality, and then also revealing Mars as a dynamic planetary system. The document also recognizes that we're in an inflection point with this program. Mars sample return is a costly flagship mission, and most of the budget in the last few years, and as anticipated to be in the next few years, heavily skewed towards getting MSR finished. And so within that time, it does mean that there's slightly less money to do Mars exploration as we have been seeing it for the last couple of decades. This future plan, therefore, focuses on the conduct of smaller, more targeted missions that are able to be flown at a greater rate than some of the bigger missions we might be accustomed to. I'll note that document does not really talk too much about advanced nuclear capabilities, but in large part that is because those kinds of development efforts are not under the purview of the Mars exploration program per se. They're actually held in other parts of NASA, other directorates within NASA that are focused on technology development across NASA. The graphic here on the right is part of the future plan published by NASA. And on the left, it asks the very simple question, where do we want to be in 20 years? What do we want to be able to do? We want to be able to get to compelling places, do systematic studies of Mars the way we are able to do them here at Earth, and make sure that we can get back as much data as possible to maximize the scientific return of our missions. And so the right-hand side of that chart talks about how we enable that. How do we get there? And so that is through things like more affordable opportunities for flight missions, making sure we have the appropriate infrastructure to do all of the Mars missions that we want to do, make sure we're doing the right targeted technology development, and make sure that we have a diverse community of people, scientists, engineers, and others who are all having a say in how we go forward. This is another graphic from the future plan, and this helps to contextualize again how this is approached as a strategic endeavor. So on the left, you see some of the outcomes that have been achieved from the last couple of decades of Mars exploration. And so that's things like following the water, getting into habitability, looking for life, getting ready for humans, things I've already talked about a bit. And then towards the right, you see how we anticipate being able to build on those things in the next couple of decades, where we're able to access materials such as ice that have not been something that we've been able to do just yet. Making sure that we're able to continue to access a broader array of surface and subsurface environments, making sure that we're leading the way in science for human exploration, getting to places that, you know, have been hard to get to historically, and then expanding our ability to return more and more diverse materials. So now I'm going to shift over to talk a little bit about nuclear technology at Mars. This is not my area of expertise by any means, but what I wanted to talk about was a very specific workshop that I was invited as MEPAG chair to attend in December of 2023, and that is the Accelerating Space Science with Nuclear Technology workshop. This workshop resulted in a report, the cover of which you see there at the right, and it is issued by the Institute for Space Science and Development, and you can go to their website to download this report and see what it says. There were sort of twofold complementary goals. The first of those was to invite together technologists and the science and planetary science and engineering community and get those groups talking to each other and understanding each other's needs. So the first part of that was making sure that those of us in the science community across the solar system, not just at Mars, understand what advances are being made in nuclear technologies, both for propulsion and for power generation, so that we could think about how those things might be used for deep space exploration. And then conversely, knowing all of that, we got into breakout sessions and talked a lot about how we perceive those technologies benefiting deep space science. And so how we would use them to really, again, enhance and grow our ability to do deep space science at NASA. There were 5 major topical outcomes of the workshop, not all of which are directly important to Mars exploration. A lot of them relate to things like being able to improve capability and access to outer solar system destinations. Examples of that are, you know, being able to minimize the number of gravity assists because you have the power to get to where you need. And that means you get there faster and then you can do more science when you're there. Nuclear propulsion has the ability to also increase launch period flexibility. Planetary launch periods are one of the biggest constraints on our ability to fly all the missions we want to fly, because you can't always launch whenever. You have to, you're at the whims of physics, and they're not really whims, they're just irrefutable laws, and you've got to work around them. And so being able to expand our launch periods gives us a lot more flexibility. And an example of that is in the decadal survey, for example. I think the outer solar system folks would really, really have liked to had prioritized a mission to Neptune. But unfortunately, the launch periods are very, very restrictive for the foreseeable future. And it was simply determined that that was just not a feasible mission to prioritize at this point in time. And so in its stead, the Uranus Orbiter and Probe mission was prioritized. It's a wonderful mission. It will return wonderful science, but it's a little more accessible in the time frame that we were talking about with the decadal survey. The other advantages come with being able to have the power to launch bigger, more massive systems. With more mass, you can include things like more radiation shielding, and that is important to being able to deliver the science payloads and have them keep working as long as possible. Increased power can also be used to increase communication rates. To be able to transmit more data faster enables us to do that much more science. It also enables us to operate instruments that require more power. Power is a huge constraint on spaceflight systems, both operating spacecraft and operating instruments. And so again, I've touched on this in other ways, but getting more capable vehicles to distant locations is always going to be a benefit and help us do the science we really want to do. Now, there is a caveat that goes along with all of this that we recognized as part of this workshop, which is that in order to take advantage of these technologies within the current framework of NASA budget realities, we concluded that these systems cannot be so expensive that they dramatically change the cost profiles of our missions, making them much larger and more costly. These systems need to either be very affordable or they need to be provided in a partially subsidized manner so that the mission costs don't dramatically increase. Where for example, $800 million orbiter to Mars, may get a power system or a propulsion system that would make it far more capable. But if it makes it a $2 billion mission, then that's no longer feasible. So we all agreed that in order to achieve this, the development of these systems really needs to look for the commonalities between mission applications, not just deep space, but all markets. That includes things here on Earth, and then make sure that we're designing in such a way that we can realize economies of scale and keep costs down, especially for the deep space applications. Okay, and here is my one woefully inadequate descriptor of human exploration of Mars. Really, this is to touch on a topic that I know is important to this audience. But Moon to Mars, as I said, the vast majority of it has been focused on lunar exploration right now, the Artemis program, getting that off the ground and successful. But fundamentally, this is a long-term plan for exploration that includes sending humans to Mars. And I think it's really important to understand that NASA has defined this program as having 3 pillars that are all equally important. And science is one of those, and that's really wonderful to hear. National posture and inspiration are also incredibly important aspects of why we're undertaking this activity. The document that you may or may not be aware about is the architecture definition document. This is the primary publicly available document that outlines things like the objectives, the needs, the capabilities that systems are going to have and need to have, not just to get to the moon, but also to get to Mars. And what it does is it outlines and guides decision-making, and it identifies important factors that flow down from one decision to the next. And it helps identify the decisions that need to be made first because they have so many knock-on effects. One of the things I'll point out, this architecture definition document is well over 400 pages. There are white papers, there are ancillary materials. There's a tremendous amount of information here that I couldn't do justice to, even if this whole talk were about the subject. But on the right is an example of priority decisions that need to be made for Mars human explorers. And so on the left of the dotted line in this diagram are decisions that were identified in the 2023 version of the architecture review. And so you can see that they relate to kinds of different topics. Mars science priorities is right there in the middle because what science we want to do is going to dictate a lot about the number of people we need, the power systems we need, what we're going to, what cadence we're going to do all of this on. On the right-hand side, you see decisions related to other aspects of such missions like planetary protection, how long we can have people there, and so on. And so these were added in the 2024 version. And so we expect to see more coming in. This is an annual process, the updating of these documents. And so the details for Mars are starting to get fleshed out more and more. And I expect that we'll see more details about Mars in the coming revision in the first quarter of next year. Integration of all of this with the actual science community of Mars scientists has been a little hit and miss sometimes, but I think we're making a lot of progress there. Part of that is due to the fact that the science community resides in a part of NASA that is purely devoted to science, the Science Mission Directorate, whereas the Moon to Mars program is part of the, Exploration Systems Development Directorate. And so getting communication across those borders takes a little bit of effort, but I think we're getting there. Okay, so I'll start to wrap things up by talking about the budgetary outlook. I think I'd be lying if I didn't say that we're facing a very uncertain future right now. The Science Mission Directorate at NASA, which is responsible for all deep space exploration, and particularly of relevance here, the Planetary Science Division, really hasn't experienced the continued investment in deep space exploration that the decadal surveys, not just the planetary one, but all of them have anticipated. A lot of that is due to the fact that we find ourselves in a recurring situation of continuing resolutions and delayed budgets from Congress. And that typically ends up resulting in flat budgets. And then once you account for inflation, those flat budgets are really cuts. And so we're really not making forward progress. We're sort of treading water at best. And an example of that is the review and re-architecting of Mars sample return that has somewhat stalled because of our inability to get commitments on budgets. Also factoring in here is that the president's fiscal year 26 budget request, or what I'll call the PBR, would cut NASA science overall by nearly 50%. It is aimed at canceling more than 24 missions across NASA science. And specifically with respect to Mars, it would cancel Mars sample return, as well as 2 ongoing missions, Mars Odyssey and Maven. And I think that latter cut is especially painful because these are missions that have been tremendously successful. They're still returning great data, and they are pennies on the dollar for what it would cost to fly new missions. And so the idea that we would turn them off before they're absolutely incapable of doing anything else is something that I think is deeply unfortunate. Now, when we look at the appropriations process in Congress, the House and the Senate have gone through their initial appropriations markups of the president's budget request, and they would largely reverse these cuts in planetary science in particular. But until we have a fiscal 26 budget, NASA is generally expected to plan to the president's budget request. So that's led to a really high degree of uncertainty in the last several months about what would be happening now that we're in the new fiscal year, what to expect. And that's caused a lot of concern. Certainly the government shutdown that we're all experiencing right now, and then the continuing resolution that is expected to come out of that only add to that uncertainty. And then another factor is the fact that OMB has dictated that they may not spend the money as enacted by Congress. That said, my last slide, I don't want to end on a down note. There are positive signs. It's been reported that immediately prior to the shutdown, the acting administrator, Sean Duffy, directed NASA headquarters to plan to the lower of the congressional markups, and that's the House markup. And that actually includes $300 million for MSR. Overall, there's strong support for Mars exploration and planetary exploration in general in Congress and in the public. I think it's a major driver of science and technology in this country and is really a source of leadership in the world. And, I think we can't discount the strength that comes from the fact that the exploration of Mars in particular is something that is tremendously inspirational, especially as we look towards Mars sample return and human exploration. Thank you very much. Be happy to answer any questions you have.
Thank you. We have time for maybe 1 or 2 questions.
Yeah, hi, this is Robert Suprin. I'm president of the Mars Society. One thing that really dismays me about the plans that you presented is that they seem to be based on fixed ideas. I mean, for example, if you take the new reality, right now, there are 3 Falcon 9s being launched into orbit every week. Every other day, there is a Falcon 9 being launched. Okay, in the past couple of years, they've launched more satellites into orbit than all the other satellites that are there put together from the entire human race since the dawn of the space age. Okay, and yet we're not looking at this capability for the planetary program. These things could send each one 4 tons on trans-Mars injection. So if you size your missions to the capability of this launch vehicle, you could be launching many probes to Mars and also Venus and wherever. Okay, and I mean, you talk about this $10 billion Mars sample return mission. With the same money, you could do 20 $500 million missions, or missions averaging $500 million each. Okay, and I mean, really, you say this is the conclusion, this is the top priority, but it just kills all other missions. If instead of doing that, you could do 20 missions with rovers and helicopters and life detection experiments and drillers and ground penetrating radar orbiters and you name it, all over the place. I mean, if imagine you were an alien scientist wanting to explore the Earth. Would you do it by saying, I want 1 rock from 1 place, or I could send 20 expeditions to 20 different places across the globe? Okay, it doesn't make any sense. It just seems that you're operating from fixed ideas, and we certainly here in the Mars Society absolutely oppose these cuts and destruction of the planetary program. Okay, but you've set yourself up for it by saying we're going to base the whole Mars program around the Mars sample return. It's $10 billion or it's nothing. And I say, well, it's nothing. Well, anyway, what's your response to that?
Okay. I actually disagree a little bit with the premise that we're not considering alternatives. I think I've mentioned a couple times through this presentation greater integration with commercial service providers. That is something that is absolutely in the future plan for Mars. That doesn't mean that all of a sudden we have a lot of money left over. I mean, it still costs money to launch things, and you have to have the money to have a payload to put on there, and you need to spend money to develop those technologies and advance them. I would argue that MSR is not the only thing that we are doing. Again, in the Mars Future Plan, I talked about the fact that we're looking at doing other missions even during its peak spending for MSR, and that those are more frequent cadence missions. That is the objective that's laid out in that future plan. I don't think anybody has argued that we should only do MSR and nothing else. We all recognize that the current iteration of MSR is going to one place. We've chosen the best place we think we can that will return the greatest amount of science we can get from a single location. But we certainly anticipate that a benefit of human exploration will be the ability to go to other places and bring back greater masses of sample. And we can intend to continue having robotic exploration of Mars. So the question is how you marry all of those things within the realities of financial constraints. And there will always be differences in opinion about what our priorities should be. But I think it is fair to say, and I say this as a person who has made her career doing robotic exploration of Mars, that, I can also simultaneously appreciate the tremendous value of something like sample return in advancing our knowledge and helping us define what that next generation of robotic exploration should look like and be focusing on. Thank you for the comment.
My question is about the compelling places that we should go to in future missions. In the past, planetary protection considerations seem to have kept us away from some of the places where life is most likely to be found, in addition to sterilizing instruments, which always seems like a good idea. Do you see that changing, that we can actually go to places where life is likely to be found? Hard to justify a billion-dollar mission to find life if it can't go to a place where it's likely to find it. And following on that, in your view, where should we go to find life if we are allowed to? Should we drill into subterranean lakes if we're able to? Should we develop that ability? Should we send robots into caves? Should we go to places where there's evidence of recent surface water flows? Or what are the most promising places to deploy our limited resources to look for life in the next 5 or 10 years?
So I think the decadal survey, again, addresses that topic very directly with its prioritization of this mission concept called the Mars Life Explorer. The concept that was developed by the decadal survey was for a medium class mission. So we're talking about $1 billion, $1.5 billion, and there was a detailed cost analysis done that you can find in that document. But that mission would target mid-latitude or low latitude, so to speak, ice deposits. And ice deposits are historically a place that are considered, sort of on that continuum of places that, gee, do we really want to go there? But that mission, in fact, advocates for going to a location where there is near subsurface ice, drilling into that ice. It is a short distance drill, few meters. But being able to actually extract it, do down borehole measurements, and look for life with a suite of somewhat, what's the right word to use? I mean, they're not the all-encompassing best possible ever, instruments that you would send. It's got to be consistent with that budget. But, that would be the first step in looking for extant life at Mars. And I think there have been a lot more conversations going on in the Planetary Protection Office at NASA about how we do exploration in such a way that we protect both ourselves and Mars, but get to those science questions that we really are that are really driving the exploration that we want to do.
Thank you so much, Dr. Hamilton. Thank you for your time today and your presentation. We really appreciate it.
Thank you.
David, can you hear me? Am I coming through on your end?
Hi, yes, I can hear you loud and clear.
Okay, excellent. So we're running a little late today. We're going to roll into the next speaker, everyone. So this next speaker is David Malott from SpaceFactory. Take it away, David.
Okay, thank you. Can you see my screen all right?
Yes, looks good.
All right, let's wait one moment. Okay, thank you, everybody. It's delightful to be here. So I'll be presenting what I call the architecture and engineering of survival. So how does SpaceFactory believe we can build on the moon and ultimately Mars? So, I was drawn to space, as I'm sure many of you are, because there is a kind of romance with space. But to kind of just start by dispelling the romantic and what's involved when it actually comes to habitation. So thinking about ways that space will kill you. So there's the vacuum of space, extreme temperatures, which fluctuate between the cryogenic and burning temperatures. You get, in the case of the moon, you get moonquakes, micrometeorite impacts, space radiation and solar radiation being long-term killers. Dust, lunar dust, which gets into everything, including lungs. Low gravity, which over time will have an effect on bone density and muscle. And then just simply resource depletion, going to places that aren't in the bubble of Earth and having to find ways to live off of the land. And the last one, which may be the saddest of all, is isolation. And thinking about the human psychology associated with, long duration space missions and how can architecture help to ameliorate some of that feeling of isolation, being away from planet Earth. So, and I'm borrowing this terminology from NASA. So there's sort of three classes of space habitation. Class one is, I call it landed. So basically it's built on Earth and landed like a spacecraft, and it serves as the short-term habitation. Class two are assemblies. They could be self-assembled, like the example that you see on the screen. SpaceFactory is focused on class three, which I call ground up, or another terminology for this would be structures which are built using in situ resource utilization, or ISRU. I know Dr. Zubrin is a huge proponent and a thought leader in this area. So when we look at everything that needs to go into building a habitat from the ground up, it involves having an entire robotic and surface infrastructure that's not only habitation, but power and communications and mobility. There's more than one way to do this. So as I explained, the way that SpaceFactory is doing this, just bear in mind, there are other competing or complementary philosophies about how habitat should get built. So our particular focus is via 3D printing, which is a layer by layer formation. It would be done completely robotically, and the feedstock or the 3D print material is ISRU based. So in this case, we are taking, in the case of Moon, it would be anorthite. In the case of Mars, it would be basalt. Okay, and mixing with the binder, just basically the thing that helps it stick together. There's different options for binders. We are focused on polymers. I think in the case of Mars in particular, this pathway is appealing because polymers can be, in theory, synthesized from hydrocarbons found in the Martian atmosphere. So things like HDPE, which we've been using in some of our projects, could be synthesized from Mars in situ resources. And then there's the design itself. I am an architect by profession. SpaceFactory as a company is mainly engineering focused. I think the two do go hand in hand, and that might be one of the points I want to make in this presentation. Is that we as a company started looking at the architecture with the design of the Mars habitat, and soon after found it was very much an engineering problem where the design sort of got ahead of the engineering, and we would have to advance both in parallel moving forward. So our Mars habitat, or we call it Martia, has a number of unique aspects to it. So one is just the sort of unique design that's been called sometimes an egg or a beehive. It's very much a result of trying to create an efficient pressure vessel. So one of the big drivers of the design is that the Mars atmosphere is very thin compared to Earth's atmosphere. So the interior of the habitat would want to push outwards on the structure. And then hence this very efficient egg-like form to contain that internal pressure. The other thing was this extreme temperature fluctuation, and all materials and structures will expand and contract with temperature. So the solution here was to disengage the interior floors from that external shell so that we could actually allow the external shell to expand and contract while the internal shell supporting the floors could remain static. And by doing this, we greatly relieve the amount of mass that would have to go into building this structure, as well as setting up conditions like the stairway that would occupy that space between the inner and outer shells. So a little bit of architectural innovation happening there. Functionally, Marcia is designed as a home away from home. So we did have a brief from NASA for this particular design challenge that called for both workspaces, but also living quarters. I mentioned isolation before as one of those things to really be concerned about. So the whole premise of the interiors was to design a communal experience where we would even have these windows from the inner shell. Even if you're looking at the outer shell, there's always a feeling of seeing something beyond to alleviate the confinement. Working in a skylight, even though that would compromise from some of the the necessities of protecting from solar radiation, we felt would be really important for that human experience. When it came to constructing Marcia, the idea would be it would be done completely robotically without human assistance. So the thought is that the robot would actually go in advance of the astronaut, prepare the habitat, have it sealed, have it tested even before astronaut arrival. This is a very sort of preliminary idea how it can be constructed robotically. One of the other benefits of the vertical configuration is that the robotic 3D printer doesn't have to move as much, and then we would just have a telescoping arm to take it up to its full height. We always thought also that Martias were designed to be more like clusters. So we always thought that it's not just one habitat, but a community or a neighborhood. So thinking about how these habitats would integrate with each other, but also with power, communications, and other surface systems. After the design phase came what was the much harder part, which was having to prototype at 1/3 scale the Marcia design. So what you're looking at is footage from the NASA Centennial Challenge, where we configured a robotic 3D printer, deployed it on site, and had 3 days. So this is time lapse over 30 hours to 3D print this structural shell. The material was a proxy for Martian material. It was basalt fiber and PLA. It's a very common 3D print material as the binder. And what this was meant to validate was that we can build large performative structures with 3D printing as a technology. Now, of course, that was done in the comfort of what we call ambient environments. So it was indoors, in air, at room temperature. The next exercise, and this was done a lot less visibly than the Centennial Challenge, was a partnership that we had with NASA Kennedy Space Center, which was taking that same 3D printing technology, but into a lunar environment chamber. So specifically something in vacuum, ranging from cryogenic temperature, so -200 C up to 60 degrees C, and actually on a regular bed. So having to devise ways that we could actually print on top of loose, unconsolidated material, and not having the benefit of sort of a manufactured print bed. As with Marcia, we kind of developed an architecture so that we would be sort of developing technologies in parallel to developing the architecture. We call this one LINA, basically lunar infrastructure, short for that. So the idea with LINA, it would be much more kind of pioneering than Marcia was. So imagining Marcia being a far future vision of a fancy habitat with indoor spaces, LINA is really designed to be a rudimentary shelter. It's actually unpressurized. So think of it more like a hangar than a building. And then under this hangar, then we'd have the opportunity to park pressurized modules or rovers or other surface assets. And the benefit of building a LINA is that it would provide protection from space radiation and solar radiation, from micrometeorite impact, from moonquakes, and actually help mitigate the thermal fluctuations by absorbing it into this large mass of regolith. In this particular image, you can see that the 3D printed shell is actually just a small component of the structure, which is then overburdened or covered with a little over 2 meters of regolith to provide that attenuation from cosmic radiation. Over the course of the project, we sort of took the data we were getting from 3D printing in that lunar environment chamber, using it to inform print rates, which could be reasonably achieved on the lunar surface at the temperatures of the moon. And finding from that we could complete the structure like Lena within 14 days, which for us was the critical window. So that's the lunar day cycle where we would have access to more power. What you're looking at now is one of the prints inside the vacuum chamber at Kennedy Space Center. The material is a PLA with lunar Haldemann simulant. This particular print, I believe, was not at cryogenic temperature, but you can see basically the kind of resolution or fidelity that we're able to get from this 3D printing process with a material which is mostly ISRU derived. So very importantly, these prints that were done in vacuum were then sampled and characterized so that we have data points for this material printed in a lunar-like environment, which can then be used to inform a structural design. So whereas in the Mars Habitat project, we had made assumptions in terms of what our material strength would be, here we had actual data printed in a lunar-like environment, subjecting it to gravity load, moonquake loads, and meteoroid impact loads, okay, and finding the governing criteria and developing a structural system that would meet all the safety criteria agreed upon with NASA. Okay, and at the end of the day, what this meant is that, with that material, okay, which is a combination of lunar regolith, and at this point, we're assuming Earth imported polymer, we could shave off roughly 50% of the mass of the structure compared to if we had built that same structure out of aluminum and transported it to the moon. So while the structure itself, this regolith polymer composite structure itself is heavier, because most of it, and about 80% of it, is regolith, we're able to reduce the total mass of the structure by 50%. Okay, and I think this project was very important as well for us because it did set us up on a kind of feedback loop where we would always, as I mentioned before, develop things in parallel. So we might start with an architectural concept, simulated structural behavior, test the actual construction technologies at a subscale in a vacuum chamber, test the materials that were produced in vacuum, and then actually then quantify the amount of materials and think about, well, does this actually make sense economically? So, where we were about a year ago was, in this diagram. And what this diagram is trying to show is that the kind of holy grail, I would say, of extraterrestrial construction is in the upper right-hand corner, which means something which has low launch mass. In other words, very little material imported from Earth, but also low power. And so in contrast, laser sintering is a technology that's being researched by several groups. That's very low mass in that it's nearly 100% ISRU, but it requires a tremendous amount of power. Pre-manufactured, inflatable, origami type structures, inherently maybe more low power, but high mass in terms of the whole thing has to be brought from Earth. We're sitting about in the middle right now. And I think where we're all trying to go to, meaning the industry or the research community, is trying to get to is that upper right-hand corner. So what we've been working on for the past year is moving towards that upper right-hand corner by significantly reducing the amount of polymer mass that we use to construct. And also diversifying beyond habitation to include other forms of surface infrastructure that might be in the more near term. For example, roads. So we could see a near future in Artemis where you land your class 1 habitat, but to facilitate the future developments of the lunar economy, one of the first things we feel is necessary is roads to de-risk rovers transporting things from point to point, to open up surface exploration, to be able to go farther and travel faster with fewer resources. So roads being extremely valuable. So the way we're doing this maybe doesn't sound as futuristic as 3D printing. It's a little bit more basic in the way that we are, working with, grading of regolith, reinforcing it with meshes, compacting it, and sort of just hardening the surface. So much more similar to the way that roads are built than a fancy 3D printed structure. So the first thing that we do is take the regolith and sift out the fine particles so that we're left with these chunks that are about 0.5 millimeter to 2 millimeters. So it's still small, smaller than asphalt, but something that can still interact with the scale of a mesh. Okay, so we sift out about 85% of the fines, and we're left with the material that can then engage with the geogrid. And here you're looking at some examples of that. Now, the benefit of using the geogrid is that we can pack it flat, but then origami style, it can fold up to form these three-dimensional buckets, which you see here. And just by doing these two very simple things, by size sorting the regolith so that we get larger particles that can interact with this mesh window, we're able to increase the bearing capacity of loose regolith by 16,500%, okay, with only 1% or 1.2% Earth imported mass. So very, very effective in terms of leveraging ISRU to get you almost all of the way there to be able to construct roads, but also three-dimensional load-bearing structures. Okay, and what we found is that we can begin to combine these two techniques. So you can use this geogrid and regolith, soil stabilization method to build up load-bearing walls, but you can't quite form a roof with this method. So we turn back to the 3D printing with regolith composite as a means to build just the shell that you need to cap the vault. And so we're about 50% of the way built up with just the wall, and then the remaining 50% would be 3D printed, and then the whole thing covered with regolith. Okay. And so the critical aspect here is being able to design that wall to have enough bearing capacity to accept the vault, which goes on top. So we performed the structural analysis, came up with the number 135 kPa as a target, and then basically tested different grid configurations and packing densities to make sure that we achieve that target bearing capacity, and found that we could with quite an amount of safety margin. And by doing all this, we were able to reduce the amount of imported mass to about 25% of an equivalent Earth manufactured structure. So now we're getting in the realm of really significant cost savings that would justify the technological investment in ISRU construction because of the mass savings that we can offer compared to those class 1 or even class 2 landed and assembled Earth manufactured structures. Okay, and then on top of that, we've developed methods to surface that material which I just described. So this would be the size sorted and compacted regolith, but mixed with a much smaller percentage of binders. So we're going back to that polymer route and heat curing it. At this point, we're doing it with infrared. We're going to be moving into solar heating as a means of fusing it. You know, internally, we call the material lunar asphalt because it is a lot. Kind of process-wise, very similar in that we are dry coating like powdered polymer onto the regolith. So it's not heated, I should say, it's not the way 3D printing is, in which it's sort of heated and extruded, but it's laid dry and baked, essentially, to create this very hard surface. So in a phase 1 of an STTR, we paved out a road in a vacuum chamber and tested it in vacuum by driving a wheel back and forth on it 100 times, okay, to simulate a rover traversing over this road. So you can see some images here of the paving apparatus. You can see in the middle image that lunar asphalt feedstock, which has been fed through this auger system, spread out and leveled and then heat cured, as you can see on the lower right. Okay, I think we're able to achieve a decent processing rate as well. So doing about 1 meter in every 10 minutes. Here you can see the wheel mechanism used for testing. This is, you know, this is filmed outside the vacuum chamber, but just to give you an idea of the test apparatus. Okay, and then the benefit, you know, the comparative benefit of the road. So these images show that same wheel driving on uncompacted, so just loose moon dust and just accumulating a lot of dust on the wheel. Even with compaction, you can see dust accumulation, and we're still developing ruts. Okay, so for those of you familiar with like the Apollo missions or, you know, ongoing NASA you know, R&D into lunar exploration, lunar dust has been cited as probably the most challenging thing to overcome because of the rut formations, because it's very, very sticky. It gets everywhere. It corrodes systems. So dust mitigation, hugely important. So this is the benefit of the road. So this is the wheel after 100 cycles of driving back and forth on the road on top of a bed of loose lunar regolith. Okay, and zero dust accumulation, zero rut formation. We took samples of that road, brought them outside the vacuum chamber for testing. Far exceeded the capacity that we would expect for any kind of rover in the foreseeable term. Okay, and I think it sort of checked out all the buttons, or at least set a new baseline, I would say, in terms of launch mass. So now we're down to 1.4 kilograms per meter. Or sorry, 0.14 kilograms per meter. Processing rate approaching 7 meters per hour. And a reasonable power consumption. And given this was done with the infrared heater, and if we were to use solar, which we think should be workable, we can drop the wattage even further. So what this all means is that we feel that we can actually make a kilometer-long road with the payload available, you know, in the kind of near-term Artemis scale. So not the SpaceX Lunar Starship, but more of the Blue Origin 10-ton, 5-ton lander class. Okay, and then finally looking at the economic benefit, the analysis of doing this, we think in particular roads have a lot of benefit. So if you think about the cost of lunar rovers, you know, just the manufacturing cost, but also all the R&D cost, and the fact that most of the rovers are designed only to last 14 days, which is that lunar day cycle before they probably, you know, in the case of the moon, would go to permanent sleep. In the case of Mars, of course, they've been lasting a very, very long time, amazingly. But the moon, in many ways, is harsher that way. So lunar night survivability on the lunar South Pole is an extreme challenge. So the shelter in that case, if we're using it for thermal regulation, can begin to extend the lifespan of that $150 million rover to maybe, let's say, 100 days. Okay, so you get more out of that same asset. And then once you provide roads, you don't have the things that traditionally undermine the rovers. And suddenly we can be thinking about rovers which perform on multi-year missions. So we kind of, in a way, you amortize the cost of the infrastructure through the savings that you get in your robotic and other surface assets. So that's what we see, begin to see as an emerging business plan that justifies the expense in the research and development of the infrastructure. Okay, and then finally, and I know at the beginning I sort of said let's not be overly romantic about space and to sort of be realistic about the challenges and difficulties, but at the end I think there is a very strong pull that affects all of us and probably why we're in this conference in the first place. And that is the allure and the pull of space. So just to tease what we just started working on. So this is a payload that's intended for Mars. One of the things we realized we were getting pretty good at as we were developing, 3D printing tech and that last that GeoGrid soil stabilization technology I showed is that fundamentally we've gotten pretty good at just moving regolith around. So excavating regolith, size sorting it, transporting it, conveying it, packaging it. So the idea of this payload would be for any and all experiments which want to be on the Mars surface because they want access to Mars soil. So it doesn't have to be construction. It could be for oxygen extraction. It could be for biological experiments. It could be for food, food cultivation experiments. So anything that wants access to Mars soil could be part of this, what we call HIVE. So kind of a joint venture payload experiment. And then the central portion of this can still be that test bed where we can prove out construction technologies by having these robotic arms moving around on the inside of this ring. And so just to leave it with that idea, so SpaceFactory is a small company. Okay? I think hopefully we're making a outsized contribution to the realm of lunar and Martian exploration and habitation. And through this project HIVE, we hope to invite the other small organizations, so the research universities, the other startups, even two people in a garage if they have a dream, to be able to participate in this dream of going to Mars and helping to make life multiplanetary. Thank you.
Thank you very much. We have time for one or two questions.
Hi, thank you for the talk. I had a question about the trade about your different binders that you've proposed for Mars. So I think you mentioned sulfur, you mentioned permafrost, and then there was one more. Can you talk about the trade between those different binders, what we've demonstrated, what we've tried in thermal vacuum chambers, what we can get from in situ resources? Thanks.
Sure. See if I can just backtrack to find that slide. There we go. Yeah, so various things have been proposed, like there was a Mars ice habitat. So water is a resource that's available, both on the moon and on Mars. Not sure how sort of strong or consolidated of a structure you can achieve. And of course, because of the temperature fluctuations that you would get in certain locations, it might only make sense if you're building in these permanently shadowed regions to build kind of like dirty igloo structures, but that is one option. To my knowledge, it's never been taken in vacuum. Of course, it would also have the the risk of sublimation, so it definitely has to be at that ultimately low temperature. Sulfur, we are not doing it, but I know a lot of the research community that is. I'm not sure if it's been taken in a vacuum chamber. I think sulfur, you're still looking at something like 40 to 50% sulfur concentration, and it needs to be processed at reasonably high temperature. So for us, it's intriguing, but like the polymer problem, you would have to basically find, prospect for and gather enough sulfur and refine it to be usable form. So I'm not saying no to it, but for us, it's not something we pursued. Geopolymer was the third one. This for me it's interesting. Perhaps if you're going with the route of the water ice solution, but inherently geopolymer is a wet solution, so you kind of need that alkaline solution with the water. For me, it represents issues if you do it in situ because of the boil off effect. Maybe it makes sense if you're doing it kind of in a manufactured container that's pressurized and you're kind of building tiles, which assembled. So I think that's one possible route. So I can't speak to too many of those in terms of where they are on the TRL ladder. Okay, but in terms of where we are, I think both the regolith polymer composite 3D printing and that sort of GeoGrid system, we're at about a TRL 5, okay, where we've proven it out, in lunar-like environment, 10 to the -6 torr, -200 C, and but basically at this point, looking for opportunities for low gravity demonstration or ultimately lunar surface demonstration.
Hi, David. I am so impressed by what your company is doing, and I wanted to ask a question about the beehive design. And if you already answered it and I missed it, my apologies, but I'm so intrigued by how it deals with internal pressurization and temperature variation, and I'm wondering if do you have any plans, like, is it naturally hermetic, or is there a plan to kind of seal it, how oxygen is interacting with the concrete and if it leaks through?
Yeah, a very good question. We did not, we have not yet, okay, 3D printed something and pressurized it inside a vacuum chamber and tested for leakage rates. We did something called the bathtub test where we filled it up with water and make sure it doesn't leak, but those are, quite two very different benchmarks. So the short story is I don't know. Just as an architect, I would think we would want redundancy, meaning that we should get to a point where the outer shell is airtight, but I would still introduce a bladder of some sort that would act as a second redundant layer. Now, maybe that bladder could actually be used as formwork, okay, to sort of then pack regolith on and do something a little bit more like the second technology I showed you, which isn't the 3D printing tech, but relies just more on like ramming, earth in place. So we haven't revisited the Mars habitat design in a while. We actually started with it, but it's been a long time since we looked at it again. But that would be where I would start. Would be 3D printing a pressurized vessel and then testing that in vacuum would be the first thing. And then the second thing would be looking at how we might do that in conjunction with an internal bladder.
Thank you very much. Thank you for the presentation. Thank you, David, for your time.
Okay, thank you all. Sorry I couldn't be there in person, but hopefully I was able to give you something useful.
That's good. Yep. So just go down.
Yes. Okay, our next speaker is Luther Beagle. He's a consultant who's had a long career at JPL, where he worked on the Curiosity team and also at Northrop Grumman. Welcome.
Thank you. Thank you very much for being here. So the name of my talk is Why, and we'll talk a little bit about what that means in the next couple slides. But if you take home anything from this talk, it's how long is it going to take from right now, if we want to go to Mars, and we all want to go to Mars, we understand the importance of it, we're all here in the Mars Society, we enjoy it. How long it's going to take to get from today, when they first write the first check, to actually boots on the ground? How long is that process going to be? And that process takes a lot of things into account: physics, engineering, and human factors, and hopefully you'll understand why that is. And the reason I say all this is that I'm not sure if you listen to the Red Planet Live, but it's a podcast put on by the Mars Society, highly recommended. The best episode they have is the April 5th, 2025 episode. Just happened to be the one I was on. But at the end of that, I was asked if I wanted to give a talk. And this is, I think, my third talk at a Mars Society conference. So you're right after COVID, and I think one right before. And I asked them what they want me to talk about. They're like, we're going to leave it up to you. And I'm like, oh, that's great. That's also a lot of pressure. So what do I want to talk about? I heard Elon Musk talk about how we're going to have, after Starship 11 goes off in the next couple of weeks, that we're on pace to have people on Mars in 2030. And every time I hear something like that, I'm like, I just don't believe it. I've done the studies. I've talked about it. We've thought about it. There's a bunch of studies out there. Let's actually talk about what the actual number could possibly be. And at the end of this, I don't really put numbers on any of this stuff. You'll be able to see and make your own conclusions on how long it's going to take. But it's a little bit longer than the 4 years Elon just said a couple months ago. One of the things NASA is very, very good at, and we saw this in Vicky's talk earlier, is doing studies. They've done studies for years and decades, all the way back to when von Braun was in charge. There's a wonderful book out called Humans to Mars, 50 years of studies to how to get to Mars and what to do on Mars when we're there. Highly recommend looking at it. It talks about different processes and what we have to build and how we have to build everything and what it's going to look like and how it changes with time. So if you go online and you look up Mars studies, one of the first things you'll see is studies from the 50s. This is von Braun's concept of how to get to Mars. There were studies in the 60s that showed after we actually started launching people. We hadn't launched anybody by this point. These are studies that show, okay, well, we can do this. We can have a rotating thing. All of this is physics. So let's go and start thinking about this more and more. One of the things that I did way back when in the late aughts, early 10s, is there's a series of Mars-related architectural studies called the Design Reference Architectures. This is reference 5.0. They even go back in and add in addendums to previous studies. I was associated with DRA 6 and 7, which I don't think either one of them ever got published. I couldn't find them online. But basically, they build on everything else that's going on. And what they do is they look at everything that has to happen, engineering, physics, science-wise, going forward to get to Mars. And this is one of the concepts. And if you go back and look at all the DRAs, you can kind of see which part of that architecture is the same through multiple different studies. And then you start understanding things. And as we learned more things, as we landed Viking, as we landed MER, as we landed other things and had orbiters, you kind of see what we started learning stuff and then how that changed in the design architectures. It's a pretty fascinating thing. I don't suggest reading the entire book. It's like this thick, and it's got stuff in there that's no longer relevant. The NRC right now is doing a strategic study for the humans exploration of Mars. When we send humans there, what are we going to have them do? Are they going to just sit in their rooms and play Call of Duty all day? Or what kind of science are they going to do? The NRC is studying this right now. And then we all seen this journey to Mars that's out there, and how we're going to get from here to the moon, to Mars, etc. And all these studies are out there. And like I said, this is the one I worked on for a long period of time. Back when I don't think we were allowed to work on studies to Mars. I don't think we were allowed to say Mars in terms of humans back in the early Obama administration. These things changed. But why did we do the studies? You saw Vicky's talk today. Vicky had all the results from a whole bunch of different studies. This is the study here. This is the study there. We do them for 3 different reasons. One is we identify technology that has to be developed. How do you land? How do you get people out? How do you move things around? How do I detect life on a surface? How do I just take a picture on a surface? How does that technology has to be developed? And the sooner you start, you've got 15 technologies that people have just thought of. They whittle that down to like 3 or 4 technologies that actually can go help out, and then eventually they select one that goes on. Puts reasonable cost constraints on future work. Reasonable cost constraints may mean an order of magnitude. But if you tell me that Mars sample return is $1 million, and I've got a $10 billion study in my backyard, I'm going to believe the 10 billion over the 1 billion. It gives reasonable cost constraints on future work. You're able to plan future missions and budgets. So as you can see, when you think about how we're going to get to Mars, we got to do this, we have to do this, we have to do this. And there kind of becomes an order to what the measurements have to be and how and the engineering has to be to get to Mars. Before we can do the talk that was previous to this, build these wonderful 3D structures, you actually have to get people on the surface, and you got to get that machinery on the surface. And you're able to plan future missions and budgets by understanding what goes on. The last thing is things change with additional knowledge. Every time we go to Mars, we learn something, and we put that learn something back into the future studies so that we understand what we do and don't have to do going forward. And that really changes things with time. So we've seen this before. There have been many, many studies on what you have to do before you can get humans to Mars. One of the fun things, and I use fun in quotation marks, is going back and looking at the MEPAG reports. They're about every 5 years on humans to Mars and what measurements have to be made and the priority of these measurements. I got to the point at one point where I could tell who was making the priority decisions, and I knew what they were doing because of how the priorities would change. The measurements seemed always to be the same, but different things go up and different things go down. People that do a lot of work in inhalation and working with fine particles always put dust at the top. Other people, radiation experts, come in and they say, no, radiation is much more important than dust. So let's move these priorities around. But they're all in there, and you can kind of see it over time, and you kind of know what you have to actually measure before you can do a human to Mars. So 3 things that are absolutely need to be done by precursor missions before we could launch anybody to Mars. 1, you have to understand the dust. You're going to breathe that dust in. You're going to eat that dust. You're going to that dust is going to get in your instruments. That dust is going to get in your machinery. What is the dust? How is it going to kill me? How am I going to keep myself from dying from the dust? Which is really important if I'm the one going. Radiation effects on humans on the surface and in interplanetary space. We kind of understand what the radiation environment is between here and Mars, and we kind of understand what it is on the surface. We've measured it. The problem with radiation is not the primary radiation that comes in, the galactic cosmic rays, the solar particles, other things that you're going to, gamma rays, X-rays, things like that. But it's the secondaries that are caused by things that come through and hit. So I can have shielding for humans. I can make it 20 meters of aluminum, and I'll be protected from everything. But 20 meters of aluminum is really expensive, and we can't do that. So we're talking about making things in to a 1/4 centimeter. And so how do I protect people from the radiation and not create secondary radiation? So if you look, there's a really good figure that I didn't put in here of a solar particle coming into the Earth's atmosphere. It breaks off into 2. Each one of those breaks off in secondaries, and then you get down to the bottom and you've got a whole different radiation environment on the Earth than you did up at the top. And those secondaries are really important, and you want to make sure you understand the radiation environment for the humans, because they're going to have to be out in space for, if just to get there, it's going to be a year. You have to design and test landing systems for humans. Things scale. Right now, we're very good at landing big, giant, maybe 1,000 kilogram rovers on the surface of Mars, but we can't take that landing technology, the sky crane, and scale it to something bigger. It doesn't work. You're going 40,000 kilometers an hour when you hit the Martian atmosphere, and you got to go to 0 miles an hour in 8 minutes. Dumping all that delta V is important. Design and testing of the landing system for Mars. And testing is really the key here, because I'm not getting anything that hasn't been tested. I trust you. I trust the engineering. I trust your models. But I want to see the thing that has worked before you're going to get me on a rocket, a bomb, and send me off and have me land. I'm not going to trust the models. I want to see actually some of it work. So cost, schedule, and risks. I'm going to talk a little bit about missions and mission concepts right now. Cost, schedule, and risks are all interrelated. For a typical mission, you're given a cost and you're given a time that it needs to launch. And then from there, you can understand what your risk profile is. Now, you can play around with these knobs if you want. You can make a mission that is, I want to make a mission much less risky, sending humans to Mars. That cost is going to go up because you have to do more testing, you got to do more design work, you've got to really understand everything much better. Risk goes down, time and schedule goes up. In the past, we tried to do this low risk thing, and they're doing this in clips right now. This was faster, better, cheaper, where I'm going to reduce the cost of everything by order of magnitude or so, but I'm going to increase the risk. So I get a lot of risk going on, increased risk, but the time schedule goes much less than that. But these things fail a lot more. The CLIPS missions, the success rate hasn't been the best, but they're getting better because they're learning and they're being able to go on and make better missions. So there's a relationship between dollars and knowledge too. You get a science return. This science return is however you want to define it. To fly a brick costs an X number of dollars. We know this. If it's a one-off mission, I can tell you approximately how much it is because of Phoenix and Insight. To land a brick on the surface is going to cost that much. If I fly multiple missions, I get economies of scale. That number will go to the left a lot. But all those missions have to have a backbone that really changes how you can actually do a scientific mission with what you have. For landers, there's a certain science return for different costs. You can go in and turn your knob a little bit and say, I want a little more science. I'm going to put a little more money into this. But the science is going to come to this much, because if I land here and I can't get to that rock over there, and that's the best rock in the history of Mars, I can't get to it, it's really not going to help me out. I'm stuck within wherever I can reach and whatever I'm trying to measure. So I can increase the cost of these missions by putting like MER-like rovers on, and then actually be able to go to this rock. It does cost more. The science does. You can change it around a little bit. You get more science. It does cost a lot more money. And you can even do this with MSL-like rovers. Again, let's get a big rover. This costs $2–3 billion. The science return will be even greater because you've got better instruments, but the cost does go up in this way. And I tried to put on this graph sample return, but I couldn't put the graphs in a way that made any sense to me because the sample return is way this way. You can do stuff with sample return you can't do on any rover, on any lander, on any orbiter. You bring it back, you have all the time in the world to change your instruments, to move your instruments, to modify your instruments based on everything else. These instruments here get sealed into what they can do and what they can't do. 6, 7, 8 years before the mission launches, sample return, you can change everything on the fly. But sample return also does cost a lot more, as we've seen and we've talked about with this $10 billion concept that's been floating around recently. So when you're trying to plan missions and you realize you have to do so many different measurements and you have to do everything else, there's this concept of budgets, and this kind of goes back into human factors on how I'm going to plan out the entire mission concept. I get different missions, they cost different amounts of money. A $1 billion mission doesn't cost $1 billion in any 1 year. It can cost like $200–300 million, and it goes back down. You get a more complex mission, that cost goes up. You get even a more complex mission, the cost goes up here. All of these things add together, and this is basically a wedge. And all these wedges, when they look like this, what this means is I've got, what, $500 million a year I'm spending on things. That goes down to $200 million. When you see something like that, that's people. That's not anything else. So at this point, if we're doing this wedge for Mars and Mars exploration, this 2-year period of downscope before we actually get another mission coming in, all these people have to find something else to do. And that becomes very difficult. So what you really want to do is you need to be able to plan these missions in such a way that each mission adds onto each other one. We get a nice flat top at the top, and then when things fall off, then we add missions in there so that we can get people going straight across. And this is the human factor. And the reason all of these things exist, and the reason I've talked about all these things, is what about the physics? And you've talked a lot about obscure science, costs, schedules, things like that. But what are we really talking about in physics? Well, We all know this, but this has a lot of ramifications in that when we launch from the Earth to Mars, basically the spacecraft has to travel 9 months to catch up with Mars. That 9-month period in cruise, there's not a lot else going on. These launch windows open roughly every 26 months for a Type 2 orbit, and I'll talk about what that is on the next slide. But you have to plan every 26 months you can launch another mission, and you've got to be ready to go if you're going to do a whole program to get humans to Mars. Different types of orbital trajectories. Some take a long time, some take a lot of fuel, sometimes have flexibilities, and then how we're actually use them. Delta fuel is important. The more fuel you have, the faster you go, the more you have to dump at Mars, and you have to develop that technology to reduce the amount of energy you have to get to the surface. So while I can go very fast, I got to design a whole system to slow down from 440,000 kilometers an hour to 0 kilometers an hour in 7 minutes. I can do lower fuel, but then my time to Mars goes up. I have still narrow flexibility in the launch window. Some of these I can do wide, so if the mission doesn't really matter when it gets there or when it launches, I can shoot a ballistic or continue a thrust. I have these knobs to play along with. But everything is a trade study. Everything is moving in 3-dimensional space of how long it takes to do this, how long it takes to do that. Then we get to this is the most convoluted slide I have, I swear. But it explains what has to happen. This is for a scientific mission, not necessarily what I would do if I was in industry or if I was going to do a lot of different missions. But this is I'm going to go make a precursor measurement at Mars with this particular hardware. Pre-phase A studies, concept studies. Do I need a rover? Do I not need a rover? Can I do this on an orbiter? Do I need a drill? Do I not need a drill? Then I go into a 6-month, what's called phase A. This is where I'm looking at technology development. What new technologies do I need? What instruments do I have? How does this instrument fit on the rover, lander, or helicopter? And then I get into preliminary design and technology completion. That's phase B. That takes a year. Phase A and phase B take about a year. You can cut it down a little bit. You can play with knobs, add more money here, take away money there, but it's about a year. Phase C, and this final design and fabrication, that takes about a year as well. And then building everything, testing everything takes about 2 years. Now, you look at this and you're thinking to yourself, well, they must be really good at doing this. Well, the instrument I was a PI of, Sherlock, we were starting phase C. We had designed the instrument. Everything was looking pretty good. And then somebody said, well, what happens when we make the instrument and squish it? So the way the rovers fit in the aeroshell, they get squished. And when you squish the instrument, you pack it up in what's called the squish plug configuration. There's a wheel where our instrument was. So we're sitting over here in the middle of phase C, and all of a sudden they're asking us if the lasers bend. Like, no, lasers don't bend. So we had to come up with a completely different design, and that's why everything flows like this. You basically start maturing different parts of the rover, parts of the hardware in different phases, and then eventually you get to the point where you're testing, launching them, and you get phase E. Landing takes about 9 months after you launch. The first test results come back maybe a month after that. You got checkout, and then you start the technology development for the next mission. This is a good estimate of what a costing would be for a stationary lander in FY $12-ish. But then you got a follow-up mission. So we talked about precursor measurements. If I want to do what the dust is, I want to try and figure out how the landing is. I've got to make these measurements, and then I got to flow that into engineering so that you can go test it out. So if I'm going to just focus on mission on dust, I get this, I get there, I do results from the mission, and then I want to figure out, I want to say to myself, how am I going to keep the astronauts alive? How am I going to remove the dust? How am I going to make sure that filters don't clog? They're not breathing stuff in, that if they breathe it in immediately, they're going to die. How do I do all this? By this point, I want to test it out, make sure everything is good, and then I am on a different thing. So you can see from a testing of a Mars dust mitigation strategy, I've already bought myself 10 years. 10 years to just understand dust. The missions can do more than that, but that whole process takes 10 years, and there's really not a lot you can do about it because you got a 26-month launch window. Even if you cut this down by a year, you still have to wait for the launch window down there and back everything out from there. And that's where things start getting a long time. So this is what I was trying to say. You start mission here. I'm going to start writing checks for Mars. First mission, you get the authority to proceed. This could be 48 months. I launch, I arrive. The next mission, that particular mission can actually change anything about is this mission down here. That's the third mission in the sequence that can launch every 26 months. So this mission then, from this point to this point, is roughly, no, if I put it on there, roughly like 9 years, I think it was, when I did the math on it this morning. Or 13 years, hey, look at that, 13. So, and that's assuming that you get the engineering correct and you don't want to redo another engineering thing, but then you're just adding another 6 years on top of it. So these things start adding up over time, these things you have to do in an order. So now you're probably thinking to yourself, if I had known this was going to be out budget and schedule, I would have gone to the bathroom, I'd have gone out and watched the University of Oregon game, catch the Final Score football games, but it starts becoming real. So one of the things I've been doing in my free time is I've been going up after the fires in the Eaton Canyon fire. There was a rainstorm that flooded out and destroyed a bunch of the trails up there. I've been going up helping people get the trails going. This picture was taken after 2 hours of being up on the trail. I had a mask on when I was up there, and I had safety goggles on when I was up there, and you can't tell that anymore because the dust from that, just doing that for 2 hours, got on the other side of that. It's gotten in my eyes, and it's on here. This shirt, these shirts come pre-dirty now. They're already pre-stained. The dust is just miserable up there, and this was from a 2-hour time period. If you look at what the Apollo astronauts did, this is Gene Cernan in the Apollo capsule. He was out for approximately 2 hours. And if you can see this, it's not a very good picture on here, but his whole face is covered in dust. He's breathed that in. He's been out there 2 hours. He did a 2-hour walk on the lunar surface, and he's breathed all of that dust in. If that dust has chemicals in it that are bad for you, if it's sharp, if it's asbestos-like, that's really bad for your health. And if you're now on Mars and you've been on Mars for 9 months and you're breathing that in continually, that really reduces your lifespan. And we're trying not to get reduction of lifespan. So there's a whole overview of lunar dust toxicity, and you can do the same thing for Mars. The Mars dust and the lunar dust are different. Mars dust has chemical reactions in it. It's a different material. It's different gardening. Micrometeor impact on the moon causes the dust to be a certain size and shape. On Mars, it's a little different. Plus, there's different types of Mars dust that you really need to understand because they're going to breathe it in, and you need to be able to figure it out. So the dust categories for all of this, the hazard category, mechanical. We kind of understand a lot of this now because we have rovers that have been going for 10 years. We understand where the abrasion contamination can come from, effect on the equipment degradation. For humans, it'll be a little different, but I'm sure there's an engineering thing around here. Chemical, there are perchlorates in that dust. Perchlorates are bad. There's other oxidants in there as well. You don't want to breathe it in. Human toxicology is going to be bad. Operational, dust infiltration, are your filters or your food going to be clogged and reduce power? Are you going to be able to breathe correctly? You need to understand that. And biological, the lung and tissue damage, inflammation is really bad. When you go up to the mountains and you play around with that dust, you do feel it the next day. It feels like you've been in New York City, or not New York City, but a city with a lot of pollution. You can kind of feel it in your lungs. So then there's radiation. There are two different ways to get there back and forth. This is the typical one that I like. It's a 9-month cruise out, 500 days on the Martian surface, and then 9-month cruise on the way back if you bring them back. There's other orbits you can do. There's Earth to Mars, 9-month, and then there's the Mars back to Earth, not going by Venus. I don't think going by Venus is a good idea, for multiple reasons. And then you come back. But this is really 60 days on the surface, 18 months back, 9 months. You're in deep space for 9 months. And the reason why I said this before, the reason why this is important, this is one of my favorite pictures from an old paper on the moon. But a lot of stuff happens. There's a lot of radiation that happens on the lunar surface. There's a lot of radiation that happens in interplanetary space. You need to understand both what's happening on the surface and in space. You need to be able to monitor the sun to make sure there's no coronal mass ejections going on at the same time you're there. You don't want to fry in the capsule. And you don't want to really understand how your radiation protection is working. Are there secondaries? What are the secondaries? Are they secondaries high in gamma rays? Are they high in X-rays? Are they going to kill the people? This is a great ESA slide from a radiation event that happened on the sun and how we measure radiation. And you can see where on Mars, you can see the difference in actually how much they measured on the surface. You can see actually on the surface how that's changed. You can see on the moon how much you get and where you see what's on the Earth. All of this needs to be taken into account because you don't want to fry the people. Human landing systems, like I said before, about 1,000 kilograms we can land. This is the MER rover. This maxes out about 250 kilograms. You can't get much bigger than that. The airbags weigh so much that you can't launch. And then you've got landing systems here. Problem with the landing systems here is they kick up a lot of dust. The dust goes on the surface. You can see on Phoenix where the dust basically came back around and landed on the deck. You're trying to avoid all of that with the human stuff because the human is going to be much bigger than the actual thing here, the pallet lander here. On both Curiosity and Perseverance, you saw a ton of material get put on the deck when they landed from the retro rockets. It's about 100 meters up off the surface, I think, and all of that stuff blew stuff up on the surface. The take-home messages. Before humans can reach Mars, a series of missions have to take place. Those missions have to be well thought out, well planned, and they have to be done in an orderly process where you're doing measurements and then you're checking the engineering, making sure the engineering works, that you're going to keep people alive, and then maybe you want to do it again. Take the results from this engineering experiment and change everything so that you can take in any result that you found that you weren't exactly happy with. But all this takes time. It's 26-month launch window, so 3 to 5 year development time for any of the hardware you're going to do. All that starts adding up, and what you're doing is you're just pushing out when you're going to actually have people on the surface. These have to be well thought out. They have to occur so the missions are safe. And really, you're stuck with this orbital dynamics, budgets, and development schedules that determine when the first humans landing on the surface of Mars can take place. When you add up all those things together, you come up with a number in your head that's much greater than 3 years or 4 years that occasionally you hear from people that own large space companies. In reality, that number, to me, the minimum is 18 years, probably 30, maybe a little bit longer than that, which is really depressing because I really wanted to see somebody walk on Mars, but I can't figure out how you can do all of the stuff on Mars because of the orbital dynamics budgets and development schedules and get them there any faster than that. And that's it. I'll be happy to answer questions. And I appreciated any feedback since this is the first time I've ever given a talk like this before. I started it last week. So if anybody has any feedback on the talk, I'd really appreciate that as well. Thank you.
So one observation that I can make is that you have all these, none of these missions are happening at the same time.
You could do missions at the same time as long as they make sense from a budgetary perspective and they're measuring different things. So one of the things that we keep talking about is human landing is getting the pinpoint landing, which requires you understanding the atmosphere to about 10 kilometers, from 0 to 10 kilometers. You can make, if you can figure a way to make that measurement at the same time you're making the dust toxicity measurement, yeah, great. Go do it multiple times. Get that economies of scale.
There is a company that is proposing to do their own human landing systems test without any support. So that right there removes that from the timetable.
That removes that particular part of the timetable for testing the human landing. And if they do that, great. And it could possibly cut it down by maybe one of the orbital things, but you still have the dust and the radiation problem. And there's actually more problems if you read the MEPAG stuff. These are the three that I think are the major ones. Like I said, different people have different priorities when it comes to.
You can't build a lander that could do dust and radiation. Mission could do both of those.
You could conceivably do that. And that's why it's such a wide window of how long I think it's going to take. But you have to go do the radiation in kind of in the spot where you think you're going to land. You could do the dust in the same spot too. You could start pounding up on things, but that just increases the cost. And if that mission goes wrong, then you push
Well, the
back.
cost increase, things take longer.
Yes.
That is a sure way of making everything cost.
Yes.
Increase the time scale.
You have a standing army that you have to pay for.
What's the time scale, the cost?
Not necessarily way down because you have to pay for doing things faster. That's not trivial.
You know that.
I know.
An integral is
I know.
somewhat under the curve.
When it comes to
Somewhat under the curve, sure.
but when it comes to the testing, sometimes it doesn't work for the testing.
Actually, more questions right here.
Thank you.
So I have a feedback, like a small comment for feedback, and then I'm going to ask my question. My feedback is that there's a lot of visuals that weren't just graphics, and that was super incredibly helpful for me to understand what you were talking about. And my question was about secondary particle radiations. And I was just wondering if do particles spontaneously just split and form into other types of radiation, or do the other particles also have the same wavelengths as the original particle?
The answer is no. So what happens is for aluminum, if you get a neutron coming in, the neutron comes in, hits an aluminum particle, and then it breaks off into multiple different types of particles, gamma rays. If it's got neutrons in it, neutrons. So then you got to deal with the gamma rays that are coming in, and if your shielding doesn't handle gamma rays, the gamma ray is going to go through. So you get stuff like aluminum and titanium are really good at X-rays and gamma rays. Stuff with hydrogen in it is really good for neutrons and protons. So you've got to mix it up. And what we're doing now in a lot, you'll see this in a lot, is you get these layered sheets of aluminum polycarbonate, aluminum polycarbonate, aluminum polycarbonate. How long that lasts, how many shields you have to do, because it really becomes counterintuitive. I've seen radiation levels go up when you turn the radiation levels down because of Bremsschlagen, for example.
Thank you very much, Luther. Thank you. Albert, we're ready for you. Would you like to go ahead and do a sound check? Looks like you're on mute right now on Zoom. See, asked to unmute.
There we go. Can you hear me now?
We cannot hear you at the moment.
Okay, I'm seeing.
Now we can. Now we can hear you. Okay. Our next speaker is Dr. Albert Haldemann, who is the chief engineer, Mars chief engineer in ESA's Mars Exploration Group. Welcome, Albert.
Thank you. Hello, good morning there. I'm here on the East Coast, and I just need to find out how to share my.
It's the green icon with the up arrow.
Right. Okay, this is. Will it let me? Okay, the problem is I'm going to have to restart Edge to get this to work, it seems.
Okay, we'll stand by here.
Which means I'll log back in. Okay.
Okay, we'll see you on the flip side then.
I think I'm just going to check that I've got the settings right. System settings. Microsoft Edge allow recording, yes, which is what it wanted. But
Frozen.
Right.
Welcome back. Oh.
Yeah, I noticed emails. No, it's fine. Yeah. Yeah, a little bit.
All right. Yes, we're looking good now.
We got there. Good. Thank you
We
for
got
your
it there.
patience.
Okay. You have the floor.
I'll jump right in. What I'd like to tell you about is the status of Mars exploration at the European Space Agency. And we have kind of a special year this year. The European Space Agency is a treaty-based international organization. It's not a national space agency. So we have some organizational logistics that are maybe not obvious or don't conform to what people's expectations may be. We have funding approvals by the member state ministers every 3 years, and we have a conference this year at the end of November where our next 3-year budget will be endorsed, and we have various plans regarding Mars that we're putting in front of our member states. So the member states' flags are at the bottom. Along with at the right-hand side, there are 3 cooperating states, 3 associate member states, excuse me, and then Canada is the 1 cooperating state. Explore 2040 is the strategy document for the Human and Robotic Exploration Directorate's planning for the next 15 years of investments in space exploration. There's an overall agency strategy for the same time frame that includes ESA's Earth observation, ESA's Science Directorate, ESA's telecoms investments, etc. The Explore 2040 is the exploration strategy for our 3 destination targets, which is low Earth orbit, and where the objective is to maintain a human presence and utilization of LEO, the moon, cislunar space, with our ambition to allow Europeans to be exploring the moon and on the moon in the 2030s, and then for Mars to prepare for taking Europeans to explore Mars by the end of 2040s. I'll move ahead to try and catch up some time. The overall strategy's intention in the overall geopolitical context is to make European exploration robustness a little more autonomous, and to reduce risk by having autonomous projects in balance with our multilateral partnerships, and then to diversify our partnerships. Is the audio okay? Okay.
Yeah, sorry. Can you hear me?
I hear you, yes. I have a bit of a lag.
Audio's fine. We just had the microphone up here. You can't hear us down in the audience, but yeah, we can hear you great. Keep going.
Okay, great. Thank you. Okay, so the strategy's components are autonomy, reducing risk, and diversifying partnership. And then how that maps to our destinations of LEO, Moon, and Mars is highlighted here. As regards Mars, our next steps are repurposing the Earth Return Orbiter, maximizing, hopefully, the NASA contributions to the Rosalind Franklin mission, and then in the objective of diversifying our partnerships, we're planning advanced entry, descent, and landing developments and our passenger spacecraft. The priorities we have for the 3 destinations that will, from the Exploration Directorate's point of view, in front of our ministers next month in November, is to valorize our past investments, to get ROI on the things that our member states have invested in for exploration, and then to prepare the future capabilities that we need for the ambitions for Europe's participation to exploration, LEO, Moon, and Mars. Our priorities for LEO are to continue European astronaut flights to the ISS and maintain and continue the utilization benefits of the experiments there. And also, we are studying crewed transportation capability and a European-led LEO habitat. For the Moon, we are going to continue with the European contributions to Artemis, European Service Module, the elements of Gateway, our Argonaut lander, and prepare incrementally for European lunar base and European boots on the Moon. For the budget requests that we're making regarding Mars, the priorities first is to implement and complete the Rosalind Franklin mission, RFM, and to establish what we're calling the Zephyro mission, which is the reoriented mission from MSR of the Earth Return Orbiter. There are a couple of consequences that could arise from the overall funding situation and general geopolitical situation worldwide that we're anticipating, which is that some of our requests may be deferred. So it's possible that we may not get new Mars missions adopted and funded at the ministerial this year, in which case we will continue their studies in view of the next ministerial in 3 years. Another way that things happen. Yes? Okay. Another way that things happen is that sometimes the funding can be okay, it says blocking. It doesn't mean stopped. It means it can be chunked during the 3-year period. So we may get a chunking of some of the budget allocations for exploration. One of the things that is important in how we establish our exploration objectives is the exploration science. ESA has a science directorate that is based on a mandatory funding from all of the member states. Member states are required by signing the treaty to be a member of ESA that they contribute to the baseline science budget, and that establishes the science missions. But of course, the Exploration Directorate, we do science in LEO, at the Moon, and at Mars. And that science is either exploration focused or exploration enabled. And we are going to be addressing both those points with the Mars program that we envisage to close knowledge gaps at Mars, and then to do exploration science, innovative science, asking new questions, and addressing those with our future missions. So maybe the elephant in the room, but what is the status of ESA's NASA's Mars cooperation at the moment? You perhaps are aware of the status regarding Mars sample return within the FY26 NASA budget. Happily, both the House of Representatives and the Senate were, the House of Representatives at least was positive for MSR, offering $300 million in support, although that's not even close to what the annual budget was for the timely delivery of MSR, and the encouragement to look for more commercial partnerships to reduce the cost of MSR. With that still proceeding through the various legal steps, notwithstanding the government shutdown at the moment. The ESA assessment of that status is that we can't predict when the outcome will be stabilized. We don't believe that procurements can proceed for commercial providers without a lead time and a ramp up of about a year to get those contracts in place. And as I said, the $300 million is much less than what the agency was spending, what NASA was spending per year to keep MSR on track for a 2032 launch, which would have allowed a return of samples by 2039 or 2040. And while NASA is progressing on MSR, the work pace slowed this past year, and the preliminary design review that would have in principle allowed for a 2032 launch and a 2039 sample return. That's much reduced, and the 300 million budget won't get us there. In particular, the payload for the Earth Return Orbiter, the capture, containment, and retrieval system, that work was stopped indefinitely after this fiscal year without any plan to continue it next year. So given that context, and then I'll come to that in a second with our backup plan for the Earth Return Orbiter. For the Rosalind Franklin mission, the House and Senate, well, the House was silent on the specifics of Rosalind Franklin, but the Senate mentioned it directly, encouraging NASA continuing to contribute to that mission to get science from Mars in 2030 with the launch in 2028. Again, it's very positive if all of that is enacted, but the duration of the appropriation is a bit of a risk since we need to have some decisions on what the launcher will be. So indeed, we have not had the confirmation, the KDPC of NASA's Rosalind Franklin mission called ROSA, and that's the NASA project name for the cooperation. And then the issue of the executive's proposal for FY26 was to zero out Rosalind Franklin, whereas Congress is saying something different, and we're not sure how that will end up. So the ESA Mars program, what we're proposing is focus and prioritize Rosalind Franklin and get that done. We're having mitigations to allow ourselves the flexibility to wait for some of the NASA decisions. And then the repurposed ERO mission called Zefiro, currently planned in 2032. And we're developing towards that. And then diversification of partnerships with an advanced EDL mission to follow, and then light ships, which are conceived as electric propulsion buses to carry payload spacecraft to deliver them to Mars orbits and then establish the communications network. The EDL then leading to heavier and more precise landing systems later in the 2030s, early 2040s. So what's the status specifically of Rosalind Franklin? We are making very good progress to our launch date in 2028. We had a successful high altitude parachute test. That was to test the parachutes that have been in storage, the flight parachutes that have been in storage that were originally developed for a 2020 launch that was deferred to 2022 and then canceled in the partnership with Russia. So we've tested those, the storage, there's no degradation, the performance was as qualified. We are now going to also have imminently, in the next couple of weeks, we will begin a series of drop test campaigns with a mock of a structural model of the entry, descent, and landing model. That module, that's the of the landing platform. That's this time around, finally, for 2028. ESA and Europe are making our own landing system for landing Rosalind Franklin, which is a 300 kilogram rover, which was fully ready to go in 2022. We're going to be doing an egress test down the ramps that have successfully done some demos in Mars Environment Chamber now. And we're going to make some egress tests with a landing platform mock-up and the engineering models of those ramps, and use our ground test model of the rover in our test bed in Torino to make those egress tests. We're also going to do some, we will be starting in Q1, the structural model testing, the mechanical testing of the whole entry, descent, and landing module. That's the new element that we're building, and that's coming up soon. All of those things are on track then for a launch in 2028. The president's budget did call for canceling NASA support to RFM, but as I mentioned, Congress has indicated support. So we are looking for, hopefully, that the Congress wins on that one so that the partnership proceeds. The risks in particular for the cooperation are as regards NASA's contribution of the braking engines, the Mars lander engines that are derived from Curiosity's landing engines of the Sky Crane and Perseverances that were being developed for the sample retrieval lander of MSR. Those engines, the flight models, are actually in production. The funding was secured with the current fiscal year. The question is regarding the political position for delivering those next year. hopefully that will proceed. The lightweight radioisotope heater units, which we need to supplement the solar power of the Rosalind Franklin rover and the US launcher, which would be required to launch those. The mission, if we have those radioactive elements, depends on the appropriation process, which is, shall we say, at the mercy of Congress at the moment. So we wait and see. We have some deadlines when we need to pull the trigger on some decisions early next year. We're proceeding with Rosalind Franklin to its critical design review that will kick off in December and conclude in the March timeframe, and hopefully all of this converges and consolidates by the end of Q1. Zefiro. Zefiro is ESA's alternative mission for the Earth Return Orbiter, which I'm kind of parking to the side a little bit the bittersweetness of what's happened to Mars sample return. We'll wait and see. This is a mission strategic shift. We're pivoting from the Earth Return Orbiter to a dedicated Mars science mission with scientific objectives to focus on atmospheric dynamics and wind measurement, dust transport, as well as geologic studies using state-of-the-art payloads. The payload capacity of the Earth Return Orbiter is pretty large, so we have some ability to bring some payload technologies that have been demonstrated in the low Earth orbit environment, producing high resolution data sets, with the caveats that those things need to be, we would like to launch this in 2032. That's a quick development timeframe for a large instrument, and we have to get the funding approved. That will be the challenges that we have at this ministerial and in the studies we'll have to do in the coming years. We also plan to bring along some CubeSats and instruments of opportunity. And some technology demonstrator payloads are also being studied because we have a capability to deliver quite a heavy payload to low Mars orbit. We are just studying enhancing the communication system, both to meet the strategic needs for a much higher data downlink capability for a science mission than would have been necessary to support the Mars sample return operations on the ground. As well as then offering a longer-term upgraded communications capability that fits into our overall exploration strategy for Mars. We are looking for collaboration with European industries for the payload development, as well as the communication system and the CubeSats. And so those technology investments and opportunities are things that were being studied as well in the context of Zefiro. Lightship is the next step idea to have a bus that delivers payloads. We already initiated this planning for the Mars program. This is possibly or probably going to be somewhat deferred because of the funding for Zefiro, but we will take leverage of these instrument proposals that were payloads of opportunity requested from AOs that we released this past year, and proposals were reviewed. And some of the the selected teams were kicked off last month. These are them with various science opportunities defined, with the idea of having both a payload on the Lightship bus as well as a payload on a spacecraft that would be delivered to low orbit, called Spotlight. The next steps for this program are to, well, that's happened. The Lightship study that was defined. We're beginning the interface discussions with the potential for the payloads with the industrial prime contractor, potential bidders for the Lightship mission, and we will be doing one way or the other payload maturation, which we will consider how to deploy and what the priorities are after the ministerial meeting, and we understand what our budget situation is. The Lightship phase B1, so period 4 is the period following ministerial 25. That is because it is the 4th funding period since we have had a consolidated exploration program at ESA. So we will prepare a mission decision for Lightship for the next ministerial in 3 years. MEDAL is the Mars Advanced Entry, Descent, and Landing. with the objective to develop a roadmap to achieve high precision, high mass landings. So multiple tons, not just a couple tons, but 5 to 10 ton net landing in the 2040s with precision landing capabilities by Europe. So the preliminary study was completed, we did an internal study and we're in pre-phase A, intending to complete that early next year. And then we will run in period 4, so in the 27 to 28 time frame to prepare for a potential mission decision at the next ministerial. And the science definition team for metal is intended to be released early next year. So everything hinges on our ministerial meeting, our funding cycle, and we have various decisions to make and reprioritize based on what our member states decide is affordable and what they sign up for. And that's it. Thank you.
Thank you. We should have time for 1 or 2 questions. Anyone?
Is there a simple explanation for why the Earth return trajectory takes such a long time past the departure? Because that's more than 3 launch windows.
Because the Earth return orbiter is electric propulsion for most of its trajectory, and that was the only thing we could use that would fit on the existing rockets that we have available. That's it. So it's about a 2-year trajectory each way, and then then there's time in orbit in order to capture the orbiting sample. And then you have to wait for the appropriate opportunities. So if it turns out that a launch it also depends on which Mars opposition you launch at, and it turns out that the 2030 or 2032 launch windows, 2031, 2032, they're some of the poorest. It gets a little bit shorter because you can get there a little bit faster later. And when we originally proposed it, it was also a bit quicker when we were launching in 2026. We were going to be back in 2031. So 5 years, about 18 months there, a year to 18 months around Mars to provide the operations, the communications coverage for the operations on the surface for the sample transfer and the loading of the rocket, and then the tracking of the launch itself, and then the time to rendezvous in orbit with the orbiting sample. So it's about 18 months to 2 years to get there, 18 months, 2 years in orbit to support the surface operations, and then the capture takes several months. And then, of course, we have margin on that time up until when you would depart to then take about 2 years to return. So it sort of all adds up to about 5 years after launch to get back. So if you're launching but it's worse in 2032, you get back in 2039.
So according to your bio in the program, you started out working for Lockheed Martin Space. How did you end up? No?
Nope.
Wrong one. Sorry. No?
But I did work for JPL. And
yeah, JPL. Sorry, it was a. How did you end up moving from there to ESA?
So I have just through dumb luck. My father is Swiss. My mother's was American. I had multiple citizenship, which has allowed me to work both for JPL, NASA, and European Space Agency. I was on the science side of the house on the Mars exploration rovers. ESA offered me the opportunity to move to the engineering side of the house and become basically the ATLO and payload manager for Rosalind Franklin when it was getting started in 2007. Stayed with that through Trace Gas Orbiter, and then subsequently took on a more senior system engineering role for all of the Mars program, MSR, Rosalind Franklin, which we decided to call chief engineer to kind of have a correspondence mapping with the role that is similar to what I do at NASA.
Thank you so much, Dr. Haldemann. We really appreciate your presentation today. Thank you.
You're very welcome. Hope it was informative.
Take care. All right, next I will recognize Dr. Robert Zubrin for closing remarks.
Okay, so the conference is not closing now. There's still the afternoon sessions, but this is the last time we're all going to be together. So I thought I'd take advantage of it to make a few remarks. First of all, people have asked where we're going to be next year. The answer is Los Angeles. And there is a good chance that it'll be at this university, depending upon availability. But that is our goal. We're going to try here first. Secondly, yesterday we had presentations as part of our Mars Against Hunger prize competition. We had presentations from a number of teams. Now, this is a challenge that the Mars Society, or actually the Mars Technology Institute, has put out, which is this: that you see, the settlement of Mars will require a revolution in food production, because while you can do a Mars expedition without any innovations whatsoever in food production technology, you just bring your food, and you can have a Mars base that is, 20, 50 people or whatever, and support it with conventional greenhouses of a type that many people are researching, including both NASA and also in France, Interstellar Labs, Barbara Belvisi's company. If you start looking at the requirement of a Mars city, and not even a city of 1 million people like Elon Musk likes to talk about, but even say a city of 50,000 people, which is the size of Renaissance Florence or revolutionary Philadelphia, it gets completely out of control. It gets completely out of control. And the problem is, the fundamental problem is the inefficiency of photosynthesis, which is only 4% efficient in converting sunlight into chemical energy at the chloroplast level, and only 0.02% efficiency at the level of a cornfield, and 0.02% efficient at the level of a cow. And this creates enormous problems. So we're looking for a more advanced way to produce food, and this would enable human space settlement. It's fundamental to that, but if it is developed, it will answer the most persistent and greatest needs of the most needy people on Earth, which is that for plentiful food, okay? And so we have put out this challenge. The Mars Technology Institute has put out this challenge. We call it Mars Against Hunger. That is, the problem of world hunger won't be solved by critics of space exploration in the technophobic literature. It will be solved by technologists, by exactly the kind of people who want to answer the technology problems to open the space frontier. So we put out, we've created a challenge, and we're offering a $10,000 prize for someone who can do an experimental demonstration of a technology that can offers the promise of producing food at a much more energetically efficient way than it can be done by natural photosynthesis. So we had a number of presentations yesterday, and none of them met the criteria of the prize. However, there was one team that had taken a good step in that direction, so they are going to be given a prize as the best for this year. And this is the team, QR Astrobiology and Geogeology team from Monterrey, Mexico, okay, and who are working on catalytic photosynthesis. So they are the winners, not of the ultimate prize, which remains to be won. And we are going to have another round of this at next year's convention, people who can present something that offers the promise of this, and we want experimental demonstrations. But they won as the best so far. So congratulations to Mexico for winning. And then finally, just to make a few remarks. Okay, once again, this morning, as we saw last night, the incredible discoveries being made by the NASA space science program, and the credible prospects it has. And now we've been starting to see evidence that NASA may well have discovered proof of life on Mars. There's all this stuff coming in that now. There's the iron phosphates, there's the elemental sulfur, there's long-chain hydrocarbon alkenes discovered on Mars, basically oil. There's all these things that are, none of them are concrete proof because you can always find an alternate explanation for each one, but it's starting to add up. It's starting to add up. And it's potentially the proof that life is plentiful in the universe, that the universe belongs to life. Okay? This is one of the most transformative discoveries that, although, I mean, obviously it's anticipated in fiction that we will discover such things, but we haven't yet, but we're about to, if this program of exploration is allowed to continue. But yet it is under threat. One of the greatest scientific epics of all time, okay, which is the program of space exploration initiated by NASA in the 1950s, okay, which has been supported in greater or lesser degree, but nevertheless supported by every administration since Eisenhower, okay, has supported this. This is being threatened with destruction by a bunch of punks. I mean, that's all you can say about them, okay? You know, the Doge, the big balls, whatever, okay, you know, working for a person who can best be described as a complete intellectual Philistine. I mean, there's a generous, okay, it's an insult to the Philistine. No, I mean, we can't have this, okay? Look, you know, this is an epic quest. We've been looking mostly at Mars here, but the probes to Jupiter and Saturn, the space telescopes, Hubble, discovering a fifth force that is causing the expansion of the universe to accelerate, okay? And you know, there are fundamental mysteries out there, like why does the universe exist? How did it come into existence? You know, you take physics. I took a lot of physics, you know, okay, and they'll tell you matter and energy cannot be created and destroyed. Well, there's a problem with that theory. There's some matter. How is it created? Okay, it's all around you. It's in your face. Okay, there's fundamental mysteries here, and let me tell you, the most important words in science are not eureka. It's, that seems odd. Okay, that seems odd. How could that be? Okay, that seems odd. And the things that cause you to question things. And you know, 130 years ago, or more, okay, 150 years, 130 years ago, there was a fundamental mystery, okay, about the age of the Earth and the Sun. Okay, it could not be explained. Okay, the geologists said, look, the Earth has to be at least 100 million years old because we look at these processes like erosion and so forth, and we can get an idea how long it took to create features like the Grand Canyon and things like this. And there's no way the Earth is 4,000 years old or even 4 million years old. It's got to be at least 100 million years old. And physicists said that is impossible because we can calculate how much energy the sun is putting in. And we're willing to give you the thing that's made of pure coal, okay? But burning at this rate, it could not possibly last longer than 2 million years. All right? So because they were acquainted with the laws of chemistry and so forth, and conservation of energy, and sun absolutely could not be more than 2 million years old. And the geologist says at least 100 billion years ago. Now, the problem is, okay, well, they were both wrong, but the physicists were wronger, okay, because in fact, the Earth is 4 billion years old, okay, but which would have been even more fantastical to the physicists because they were unaware that there were forces of nature that were far more powerful than those involved in chemical reactions, namely nuclear reactions, nuclear fusion, okay, and yet, okay, so and how did we discover this new force of nature? Okay, when it was through astronomy, we discovered nuclear fusion. Okay, and we realized that there was more to this. Okay, and also through astronomy that we verified relativity, and it's also actually through sort of astronomy that we, electromagnetism, and of course astronomy was the source of Kepler's laws. The study of Mars led to the discovery of classical physics. Okay, all right. So there's great things left to be discovered. Okay, the processes that lead to the origin of life. Okay, it's not clear how life could have originated on Earth. Okay, especially since we find no evidence of any life forms on Earth, free living life forms on Earth, simpler than bacteria, which are extremely complex things and could not possibly have been the very first life form. Okay, and then also, as I say, the origin of the universe, the origin. Why is it that the laws of physics are been dictated in a way that makes life possible? These are things that we don't understand. And when you do understand such things, you create new capabilities, vast new powers over nature that are created by understanding the true laws of physics, the deeper laws of biology, etc. And this is what is at stake here. And then beyond that, beyond the science itself, which is enormously important, it is, once again, okay, science is the child of freedom. That's what it is, okay? And it's one of the children of freedom that freedom is most proud of, okay? Because science is the concrete demonstration of, I mean, in very material terms, of why freedom is a good thing, because it allows free thought, allows you to discover the truth about things, and this opens up incredible possibilities. And it's why a free society is grand. You know, Charles de Gaulle wrote a memoir, and I can always remember the first paragraph of it. He says, all my life I've had an idea of France, and France without grandeur is not France. What he said. Okay. Well, America without grandeur is not America. And what is the grandeur of America? We are a nation of pioneers. We are the pioneers of democracy, and we are the pioneers of science. Okay? Really, you know, people have known this for a long time. 1865, Jules Verne postulated that someday people would go to the moon. Who was it who went? Americans. Launched Florida, by the way. Okay, in a capsule with a crew of 3 that orbited the moon and landed in the ocean, was picked up by a U.S. Navy warship. So he had it right. He knew how this would have to go, that it would be Americans who would be the first to the moon. Okay, and and you look at this space age here. Okay, 26 spacecraft launched to Mars. 21 of them successful by the Americans. Okay, that is essentially 10 times as many American spacecraft successfully launched to Mars as all the rest of the world put together. And this is something amazing. This is something that people see. The human race counts on us. We are the vanguard of human expansion into space. We are the pioneers. Nobody else is going to do this, and we can't abandon this. And you know, okay, when I was a boy, I used to read a lot of classical literature, and I'll always remember this speech that Pericles gave at the end of the second year of the war with Sparta. And it's a speech over the Athenian war dead. And he says, here's your relatives, they're dead, they are heroes, you know. But what did they die for? They died for Athens. And what is that? That is a city, an incredible city that allows people to be free, and which as a result has developed all these magnificent accomplishments in architecture and drama and mathematics and philosophy. We are using the human mind to penetrate the secrets of the universe. And nobody else is doing anything like this. And he says, future ages will wonder at us, even as the present age wonders at us now. Okay? And, well, Athens actually lost the war eventually, because its politics were taken over by demagogues. But nevertheless, it's been 2,000 years and people still wonder at Athens. Okay? And I think 2,000 years from now, people will still wonder at the United States. But do we need to lose the war? Do we need to stop being what we are that makes us great, that makes us people worth wondering at? Okay? And I say no. So the thing is this, okay? The fundamental issue actually is, does America actually stand for anything? Are we here for any purpose? Or are we just here to go to the mall and buy shit? Okay, you know, I believe we're here for a purpose. You know, John F. Kennedy said, we are the watchers on the walls of world freedom. Well, one of those walls is science, and part of that wall, okay, is space science. We got to defend it. This is up to us. This is our part of the wall to defend. This is our part of civilization that needs to be defended. So, you know, we need to actually do this. We need to go out. You need to go out and visit your congressman in their home office and talk to them about this. That this is not a legitimate budgetary cut. This is an attack on the United States. And it really is, because, I mean, look, they're not just cutting money. They want to deorbit Maven and deorbit Mars, Odyssey. They can't even just leave it alone so that someone else could bring it back in 3 years. They got to wreck it. Okay? I mean, these are wreckers. Okay? There's no excuse for this. And this goes way beyond. You know, they're wrecking American scientific medicine, the Centers for Disease Control, the National Institute of Health, okay, the NOAA, okay, the National Science Foundation, and even the university system. You know, this business about getting rid of all the foreign students, okay, they're the ones that pay full tuition so that middle-class Americans can afford going to college in places like this in the state university, okay? They're the ones paying the bill. You get rid of those kids, okay, you're going to destroy American higher education, okay? Or the opportunity, it'll turn it into something like it was before World War II, where only upper-class people went to college, okay? We can't have this. So this is what is under attack, okay? Our bit here, now, of course, you're entirely welcome to intervene on these other issues as well, but the Mars Society, as such, is here to defend and advance the human exploration and expansion into the solar system. So this is our responsibility. We have to do this. You have to do this. And I hope that you will do it hard and strong. Thank you.